నెట్ ఉంది, నెట్ ఉంది. సార్ ఒక్కసారి స్ట్రీమ్ అవుతుంది నుంచి ఒకసారి చెప్పరా? స్ట్రీమ్ అవుతుందా? ఒకసారి లింక్ క్లిక్ చేయండి. నేను కనిపిస్తున్నానా? అది ఇప్పుడు కొత్తది క్రియేట్ చేశాం కదా, కొత్తది ఇప్పుడు లింక్ ఎట్లా షేర్ చేయాలంటే? హలో హలో, కనిపిస్తాం కదా, అది లైవ్ అవుతుంది. అది మాట్లాడినిపించట్లేదు కదా, అది మ్యూట్లో పెట్టండి. మ్యూట్లో పెట్టండి, మ్యూట్లో పెట్టండి. హలో, ఇప్పుడు ఒకసారి పెట్టారా? ఓకే. అయిపోయింది సార్, లైవ్ అయిపోయింది సార్. ఇంకా వర్క్ పర్వాలేదు, కనిపించిన వేరేం కాదులే, ఎందుకంటే ఓకే లైవ్ చేస్తున్నారు కదా అని చెప్పేసి ఉంటుంది, అంతే కదా సార్. స్క్రీన్ సెట్ చేసుకుంటే అక్కడ పెట్టేసేసి అదే ఇంకా మీ చేయటమే, అంటే నొక్కిస్తుంటే వెళ్ళిపోతా ఉంటాం, ఇంకా అదే అవసరం లేదు. మీరు ఇక్కడ మీ కంఫర్ట్ చూసుకోండి సార్, పెడదామా? మీకు కనిపిస్తాం బోర్డు వైట్ బోర్డు. కొంచెం వదిలి పెడితే మొత్తం
అదంతా నెక్స్ట్ నుంచి మనం ఇంకా చాలా స్మూత్ వెళ్ళిపోతూ ఉంటుంది అనమాట. సెకండ్ సెక్షన్ నుంచి కొంచెం 80% సేవ్ అయిపోతాము. ఇక్కడ ఎప్పటికైతే అసలు ఏమి ఉండదు. ఎనీ టైం అన్నట్టు ఉంటుంది. ముందుకు రండి, ముందుకు రండి అమ్మా, ముందుకు రండి, ముందుకు వచ్చి కూర్చోండి.
Very good morning, everyone. Today I will discuss about development of children academic success by systems. You see that what is agrivoltaics? Right? Nowadays we are reading about the solar PV power panels. Because of the advancements in power electronics, there is a lot of power extractions being happening to solar PV using this photovoltaic modules. We are using in this agriculture photovoltaics for agriculture purpose. When we say that it is agrivoltaics, agrivoltaic means agriculture plus photovoltaics. So, alright, so in this 21st century, we are facing a lot of issues related to this population growth. Countries like India, we have a lot of population. Because of this population, to accommodate the needs, energy needs, so you can go for this renewable energy-based power generation, then there will be a lot of scope to meet the demands of this energy needs by the population. Countries like India, we have a lot of population. and then the construction of the transportation needs of this population can be met by this smart mobility called this EVs. Right. So the energy production and transportation needs can be met by the adoption of renewable energy sources. That is the main objective of this. You see that the PVs and EVs for agricultural application. So we'll see that the design, how we can design this agricultural photovoltaics for particular application called solar water pumping with the help of MATLAB. We'll see them step by step. We'll discuss the design aspects and then we'll go to the MATLAB. First we'll design the MPPT and then we will go to the modeling of the first we'll see the modeling of the TV and then modeling of the converter and then modeling of the converter and then induction machine for the water pumping application. Then we'll see that actually why we have to do that and how we can develop subsystems step by step design guidelines on this is how we can design this solar water pumping for the agricultural applications. And in afternoon, we will see that there is a 48 different inverters. How we know that conventionally the voltage source inverters, right, and current source inverters. Apart from that, there's a lot of inverter technologies are there developed by the researchers, which can be employed for these applications. That is the afternoon session which we are going to discuss. With the help of MATLAB, we see them how we can develop. Right. So that is the objective of these two sessions today. Alright, so see the conventional why we have to go for this renewable energy based on solar. We see that basically as per the IEEE survey, what they are saying is that as on today, whatever the energy we are generating with the fossil fuels, so the same way if you are using this renewable fossil fuels to generate electricity, after 70 years, there is no availability of fossil fuels. That means that for the next generation, there is no availability of fossil fuels. That's why people are doing a lot of research on this alternative energy sources called, especially solar is a front runner. So if you can go to the extract from the power from solar PV, plays a vital role to save the fossil fuels for the next generation. So and then solar PV systems actually there is two types, right? So basically we know that solar PV cell. PV cell is the photovoltaic is the basic element which can convert our light energy, solar energy into electrical energy. So and then we know that the solar PV generate electricity in the form of DC, right? So and this DC is dependent upon two parameters mainly. One is the temperature and second is the irradiation. So whatever sun light we are getting from the solar, right? You see that like spectrum is having ultraviolet and infrared. One is causing temperature, another one is causing irradiation. These two main parameters which can affect the output coming from the solar PV. Actually, at the end, our load may be AC or DC. These loads generally needs a constant voltage. Like if we talk in terms of a DC, we need a constant voltage. But if you see that our PV module, right? So this PV module is depending upon two parameters. One is the temperature, second one is the irradiation. So whenever these two are not in our control. Right? So that load also depending upon the loads which we are using. Right? Sometimes you may need to vary them. Right? So like sometimes now we are in this room is acting as a load, and sometimes some people are coming, they are turning on the fans or some other devices. Whenever that means that load is getting changing as per the needs. And as per this, we know that in case of we have studied this MPP, right? Maximum power transfer theorem. What it says that your load resistance always must be equal to your source resistance. Then only you will be able to extract the maximum power. Right. So this load is keep on varying depending upon our needs. That is right. So but when it is changing, your source is also must change. then only we'll be able to match the RS is equal to R, then only we'll be able to extract the maximum power, but that is not happening because the source resistance is a function of temperature and radiation. These two are not in our control. Temperature and radiation is not in our control. They may vary depending upon the environmental conditions. Right. So this load is also like depending upon conditions. This load is also varying. So we need to match somehow. Right. Our load may vary, but at the same time, if you can vary the temperature and radiation, right, such a way that this RS is matching RS, that would be fine. But this temperature and radiation control is not in our hand, it is reserved by the sun. Right. So now what we need to do, we need to have some kind of a mechanism, right? Some kind of a device which can match whatever your source resistance. That is nothing but whatever temperature, whatever radiation you may have. That is giving some kind of a resistance. That resistance is always should match with whatever load you want. If you can make like that, then our purpose is met. Right? How can we do that? With the help of this power electronics. Right? With the help of this power electronics, we can make match whatever environmental condition you may have, whatever load you may have. This power converter is always taking care about matching this RS is equal to R. Right. If you assume that if power converter is not there, your RS if it's varying, that time you need to vary your RS. That is not what we want actually. Right. If temperature is increasing, if you are keeping some, if you are decreasing some load, or radiation is increasing, you are increasing the load. That is not what we want. Right. So now what we do is that this power plant converter, let us take a simple, we'll explain with DC-DC boost converter. Right. So in case of DC-DC boost converter, we know that V0 by Vn is equal to 1 by 1 minus T. Right. So we know that V0 is equal to Vn by 1 is equal to 1 by 1 minus T. This, in case of any DC-DC converters, right, Vn, In is equal to V0 by 0. We assume that losses are 0. Right. In that case, what we get, like V0 by Vn is equal to, right, so In by I0. So this will be got. Right. So this is equal to 1 by 1 minus, right, 1 by 1 minus. Now what we are finding out, I am finding out the resistance seen here. Right. The resistance seen here, this Rn. Right. So now we find out Rn. If you want to find the Rn is equal to what? Vn by In. So now we know that what is Vn? Vn is nothing but you take it. It is like V0 times of 1 minus C. Right. Vn is equal to, from this relation we got V0 is this. And what about In? In is equal to I0 by 1 minus D. That means that it will go here, then it will become 1 minus D whole square. So this is nothing but your Rn. Rn is equal to V0 by I0 into 1 minus D whole square. Right. So now what happens? Rn is equal to R0 times of 1 minus D whole square. Alright. So now what happens? This Rn is nothing but your input resistance. Rn naught is nothing but your output resistance. Whatever input resistance you may have, whatever load resistance you may have, now I have a duty ratio in our control that will match our to our source resistance to the load resistance, so that always we are having a maximum power. This is the key idea that whatever ambiguity techniques we are going to see, in all these things, the fundamental concept is this. Right. You see that 1 minus D whole square is equal to Rn by R0. So then we are having D is equal to 1 minus under root Rn by R0. Right. This is the duty ratio. Now we need to match. Right. Your temperature is varying, means your Rn is getting varied. Your load is varying, means your RL is getting varied. So whatever you have, then I can control this duty ratio. This duty ratio is in my hand now. Being a designer, this duty ratio is in our hand. That will be able to change without disturbing any other parameter. You are able to track your maximum power. That is the key idea in all the activities which we are going to employ. Right. Maybe PLO or incremental conductance or constant voltage or short circuit or no fuzzy, and even a lot of, if you see that a lot of MPPT techniques are there in the literature, but in industry generally we use a PLO technique because it is easy to implement, easy to design. then these techniques, what we need to do, we need to implement on some kind of a microcontroller or DSP or FPGAs in the end product. Right? So this is the key area lies in the abstraction of the maximum power. Right. Why we have discussed with the boost converter means, as we know that we have various DC-DC converters, classical converters like buck boost, epic, zeta, a lot of Leo converters, a lot of non-isolated converters are there, and then there is a lot of isolated converters are there. Right? So among all these things, boost is a very popular in case of solar PV power extraction because what we want, there is several reasons are there. One is that we need a high voltage. Our PV cells always typically they are in the low voltage range. Right? So you need to connect several PV cells in a series to get your desired voltage. Like you want 1000 volts of that is possible. But what you need to do, you need to connect several PV cells in a series. But when you are connecting several PV cells in a series, then what happens if there is a one cell, like this you are taking a several cells, you are connecting them in a series. But you assume that if one of the cell is gone, now it is not because of some reason, whatever reason it may be, it got now right stop functioning. Then what happens? This entire string is not able to deliver the power. That is one drawback. Yes. And another thing is that when you are connecting these many cells in a series, then what will be your effective series resistance? It's nothing but n times of individual cell resistance. If you are having a more series connection means more internal resistance. More internal resistance means more losses. Means your resistance goes down. That is what we don't want. Being a designer, always we want highly efficient systems, economical, compact, lightweight. Yes, these are the requirements. Being a user or designer, we need to have a solution to provide to our customers. Right? So this is another problem. That's why what we need to. And another thing is that when you are connecting more cells in a series, the problem is that we are going to lose safety. If you take a 24 volt system, and another side you are taking 200 volt solar PV model, which is more safety, which cases you are having more safety, you see that 24 volt systems is more safer to the customers. Right. So these are the reasons actually we are limiting to like low voltage rate, right? Because our cells is at lower voltages, right? And then we are connecting a less number of modules, like 72 cells connected in a series. If you open the data sheet of any PV module, then you will see that how many cells they are connected in a series to get your voltage. So one, this is the low, and you need typically here. Let us say we are discussing about solar water pumping application. And let us take solar water pumping, you are using a lot of machines, you have options. We always having a lot of options. When we are having a lot of options, you need to select the best one to get the best output. So we are having options called induction machines, DC machines, or synchronous, and then we have a BLDC, and then PMSM, and then sensitive electronic machines, synchronous electronic machines. There's a lot of machines which we are having. We can adapt all like any machine. But actually, we need to select a machine as per actually our application, right? Here we are having an application. Is that water pumping, right? Water pumping means we are installing our machine in very harsh environments, like we are keeping your solar water pumping for agriculture application. Actually, you are keeping your conventional land, farming land, right? There, you are keeping that means that your setup is going to be placed in a harsh environmental condition. It is not like inside your home, somewhat safer. Here it is like temperature also here because of this arrangement. In case of your home, you have like environment conditions are somewhat smooth than your PV. Right. So you need to select a machine which can sustain all such kind of a harsh environmental conditions. That is the one thing. Right. And another thing, as we are talking about for agrivoltaics. Agrivoltaics means we are selling the solution to the farmers. Right. Generally, farmers, like countries like India, the solutions, whatever you develop, it should be of cost effective. Then only we can have a market for your product. If you are making a solution, very good solution, but it is more costly, then farmers will not come trying to buy your product. So we need to keep in our mind the solution, whatever you are offering, that solution should be of a cost effective. Right. Among all these machines, you know that this induction machine is very local. For the same rating, you take a 5 HP machine. If you take this PLDC and PMSM, the problem is that they need a permanent magnet. The construction, if you see the PLDC or PMSM, on the rotor directly we are facing a permanent magnet. These permanent magnets generally alnico materials, aluminum, nickel, cobalt, right? These both they are in China. That's why you see that PLDC, PMSM we are importing from China. So the dependency is there on China, and the cost of these permanent magnets are slightly higher than other solutions where we don't need permanent magnets. Right? So this is the one. This makes these two are not so suitable for this application. Right? Although in the literature we are having it, but you see that on the field at the end they use a vaccination. Right? On the literature, on the research, you can propose with any machine. There is no doubt. But in the field at the end, if you make a product, then you need to see the viable solution among all the options which we are having. So that's why we are discussing our agrivoltaic, this photovoltaic PV pump, right, with the induction machine. And another option, if you see the DC machines, you know that if you take a same rating of induction machine and DC machine, the size, weight, value is drawback. You get a DC machine compared to induction machine, and induction is more, as we told that these agrivoltaic systems, you are placing them in your farming lands where there is a harsh environmental conditions are there. Your DC machines, if you are using for this application, it needs a lot of maintenance. Right. Now, there are farmers are not experts to do this maintenance and all. Then there is a lot of expenses they need to pay to bring the technicians to do maintenance and all these things. That is not a viable solution. That's why we are eliminating this option also. And then we have eliminated this and synchronous machine and synchronous motor. Generally, we don't prefer in this application because we need to have variable speed, right? And the cost, right? In all the cases, we have now we have one more machine left, switch to electron. Switch to electron machine is slightly costly at this moment, right? Because technology is not that much mature like your induction machine. Switch to electron machine is okay. It can also give you the mechanical output from electrical input, but the problem is that this technology is not mature and the main problem is that the input current drawing from your source is having a lot of ripples. Because of double saliency nature of our synchronous this switch reluctant machine, if you see the construction of your stator and rotor, 8 by 6, 10 by 10, different configurations are there. Stator and rotor both having a double saliency because of this. The problem is that it is having a lot of torque ripples. The torque to meet the torque demand of your machine, it has to draw currents with a lot of ripples. That is the drawback. That makes your system life goes down. Right? So whatever solution you are offering, you need to give a good life. You need to give a good life and cost effective and highly efficient. All these things are required. Based upon all these things in the field and the real time, we are preferring, the manufacturers are preferring industry for this agrivoltaic pump applications. That's what we are discussing. We will see them at the top manual also. Right? So this is the thing. Now we have seen the basic fundamental idea to extract the power from your PV at a maximum power condition. So now there's a different MPPT techniques are there. These all MPPT techniques they take care about this changing D. Whatever Rn and R0 you may have at that condition, you need to get your D to extract the maximum power. So and then we are this D we are need to apply to the power bank converter, and we are discussing about there's a lot of converters why we are going to boost. The reason is that your voltage is low and you need a high voltage at the output side. So in that case you have an option. Buck is eliminated inherently because it cannot step up the voltage. And next one is buck boost. And then we have a CAC and then SEPIC and then we have a zeta, all these things. In these cases, the problem is that we are having d by 1 minus. Right. These solutions are good if you want both stepping and stepping down, but you never require the stepping down. So, if like you see that in the dp ratio, to the gain, right? At certain below 0.5 and above 0.5, right? One case is like buck, another case is like a boost, right? Means your duty range is only 0.5 to get a boost perhaps. But in case of a boost, your entire range is giving you the boost, 0 to 1. So when you are having this more duty cycle range to get your desired boost, so then your utilization is better and you are reducing the burden on the processors which we are using at the end. Your FPP algorithms you will be dumping on some kind of a processor, the burden will be less. Right? So and if you want both stepping and stepping down, then you can think of some other option. But in solar, we don't need any case stepping down. Right? So because we have discussed several reasons, so because of that, this boost is the best option. Right? And another thing is that boost will give you, because of this, at the input side of the boost converter, we have a inductor in series. Right? Base, your input current is so smooth. Right? Whenever you know that we are like there's a voltage source, if you are connecting some sufficient value of inductance, then this element will become like a constant current. The current will be also very smooth. If you take a buck converter, the problem with the buck converter is you are having a switch and then there is a diode and then there is inductor and then there is a capacitor. Right. Your input current, if you see that input current is a discontinuous in nature. So discontinuous in nature means it will give a lot of stresses on your source actually. You like in one case, let us say I have this kind of a current. Right. In another case, I have this kind of a current. Right. Which is more good in terms of a source. This is a more good. This is having a low result. Right. This all makes us to select a boost converter in case of a solar agrivoltaic solar PV system. Then we see it in all real-time products. In case of a solar, they are having only boost converter of the PV module. Right? And then whatever based upon your load, you need say DC to AC converter. There are several converter topologies are there. You will see them and after just now, that's why I'm not touching much on it now. So these are the very basic fundamentals to extract the power from this solar PV. Right? And some cases actually we are using battery also. Energy storage also we need to have, right? Because of this intermittency nature of our solar photovoltaics, like in agrivoltaics, you may not need this energy storage because whenever you are having this electrical during daytime also you can use this pump application and get a water and just use it for your fields, right? It's not necessary that you should use water in the night. That is not necessary, right? So whenever you are having the electricity, just use it. But if you want a uninterrupted electricity, then you need to have some kind of a energy storage element. But that solution is not good for agrivoltaics because it increases the cost. Because the cost, but this one comes with the fee, right? So it is a costly solution. That's why we don't need. And also in the fields, you may not have access to the grid. If you are having access to the grid, then we are having a solution. Then you can interface your output to the grid. Whenever you are having a more power, you just sell it to the grid. Whenever you are having less power from the PV, then you take it from the grid. That is possible. But in agrivoltaics, it doesn't need all these arrangements energy storage as the grid. That's why, because whenever you are having available sun energy, then extract the power and just use your pump application. That's why. Otherwise, you can design energy storage element also, but it is the cost. We are looking for the cost effective solution due to the farmers, right? So that's where you take a converter and then you take a bigger module and then DC converter and use it on motor, right? With some additional power than if you're taking AC motor. Alright, so. And then, PV is a proven and a cost-effective technology. Like we know that there is a lot of other renewable energy sources like wind. Right. If we compare, these two are more promising among all other renewable energy compared to the wind. If you see that solar is more better because countries like India, out of 365 365 days, more than 300 days we have more sunny days. And nowadays even more than 350 also we are having a very good sunny days. So we are having a plenty of sun energy, so you can extract the power anywhere. But for the wind it is not like that. Right? You need to have a good wind speed. Right? So at least you need to have an average 6 meter per second, minimum 4, maximum like 12 something, 4 to 8 kilometer per second maximum speed. But that is possible in case of hilly areas or near to coastal areas. We will get a very good wind. But at your home or in your farming land, you may not get this much speed. So that's why PV is a proven technology for water pumping. So this PV 80 voltage. That is the reason. And then, in addition to this water pumping, there is a lot of other applications also there with the PV, like solar fencing, and they're for the making your food processing, all these things to your these things. We need to have the solar energy. We are utilizing it to process food to the animals which we are having for farming purpose, like buffaloes or fish or whatever. Alright, so and also there is a application that I said the power feed product grinding applications. We need to have this electrical power, and also like electric power egg collection and handling equipments, and product refrigeration and livestock feeders and sprayer motors for controls, compressors and pump for fish farming. Nowadays, like places like Bhimavaram and all, they're using a fish ponding, right? For the fish ponding also there is a lot of and electrical energy is needed to get a good production. So in that case also we can adopt this solar energy, right? For this farming, this is the fish farming. We can use it for the solar. And electric fencing that we have discussed like for the safety to farmland or whatever. We are using some kind of a fencing for that. We can get electrical supply from this solar PV model. There are other applications of the solar. Alright. And then another side, we need to also get a heat. We can also get heat from the solar and solar electricity. Right? That means the crop drying is very essential in case of agriculture. Sometimes we are having a crop that we need to make them dry, so you can use a solar electric dryers to crop drying and solar crop dryers and water heating, and then hot water for cleaning. So these are the various applications which we can adapt this solar. And then if you see that the statistics, here having the farming lands, and these farming lands you are doing some kind of calculation, right? And then the same lands, if you can use it for the energy production by placing our PV, then there is a, in normal case you are getting 100% output. In this case, the solar plus agriculture, the statistics says that it will like at least 186%, and more than 86% the yielding will be there. That is what the statistics, and a lot of agrivoltaics have been installed. I will show you the case studies also. Right? In the already a lot of places, the government of India and Germany, they have made a lot of pilot-based products. And they have developed and they have installed on the fields, and these statistics say that this agrivoltaics is having more than 86% of yielding compared to the conventional cases. And USA, these are the statistics from across the globe. Right? So these things you can see that in rooftop and utility PV, both the cases, we are having a very good output. Agricultural land, you see that in the this law, we are having a lot of areas where we are having plenty of sun. We can use this solar energy for this agricultural applications, right? So, and there is a various ways you need to adapt this photovoltaic in the case of the selfie or the standard of the normal agricultural systems, and then grazing, and then controlled environment you will create because of the placing the solar PV modules will be acting like a shelter to the crops which you are cultivating inside your field, all these things. So you are having a controlled environment. Like countries like you see that Dubai, and see that Israel and all these places where there's a very much huge temperatures are there, but still they are making the controlled environment with the help of the solar PV for their agricultural purpose. Otherwise, their lands are not suitable for agriculture. But you see that nowadays they are also making a lot of farming because of this renewable energy based agrivoltaic they are using. They are adopted and they made a controlled environment. Because of this PV, they are generating electricity and they are controlling the whole environment with the required temperature and radiation. Right. So that's why even Dubai also they are coming to farming. Otherwise, their lands they will not be supported to do agriculture. Right. But now because of this agrivoltaics, this everything is making possible. Even countries like Middle East, they are able to do farming. Alright, so now I see there's some design considerations like that is a topic actually. So when we make a solar PV systems, right, we need to have some kind of a mechanical arrangement, and then apart from our PV module, we need to have a proper mechanical arrangement. That actually affects the performance. Right. So what happens is that now if you are designing a low rating PV, then we will not see much difference. But now we are talking about agriculture, all these things. They are using this agriculture photovoltaics. They are certificating higher power ratings. What happens is that if you are having a ground, on this you are keeping some kind of a mechanical arrangement, on the earth you are keeping your PV module, right? So what happens is that now this photovoltaic is acting as a one capacitor plate. You see that this is a one conductor and this is acting as another conductor. If any two current carrying conductors are displaced by dielectric medium, we say that it is a capacitance. If you see the basic definition of capacitance, any two current carrying conductors are displaced by dielectric medium, there is a formation of capacitance comes into picture. This capacitance we are not designed, we are not placed, but it is coming inherently with this arrangement. Then we place a plate and we have a ground. So this agrivoltaic system needs these two, right? So whenever we are using these power electronics, right? What happens is that these power electronic converters, all these control switches, right? They are operating with PWM, right? They are operating with the PWM pulse width modulation, right? So what happens is that because of this PWM, so your right. So output is like PWM nature. If you see that inverter, let us take inverter. If we see the immediately after the inverter, if you see the voltage, they are also in the similar manner like your PWM. Are you getting it now? So because of this, what happens is that because of this arrangement, what we have discussed is agrivoltaics is having a capacitance effect is there, right? Because it is acting as one plate, it is acting as another plate because between these two, air is there. Air is also having some dielectric, so we are getting a capacitance. And because of this PWM nature, we are having this dV by dt. There is a dV by dt. What is dV by dt? If you are having a voltage like this spike line, that is a pretty fine. You will not have any dV by dt, right? It is having dV by dt 0. But when we are having the voltages like this, at this instant, at this instant, at this instant, at this instant, there is a dV by dt. Yes or no? So because of this dV by dt is there, now C is there, C dV by dt is there. So this all together causes some kind of a current. And where the current goes? The current goes from this mechanical arrangement to the ground. It is like a discharge current inside your capacitor. We are talking about the formation of the capacitance in the capacitor, right? Now this C dV by dt. The dV by dt is because of our power converter and C is there because of this arrangement, mechanical arrangement of your panels and on the ground. So C dV by dt is there. There is current, there is some kind of a discharge current flowing through this mechanical body. Sometimes if we are in case of your solar home, we like inside your home and all, you don't feel much difference because it is like micro. But we say that large rated PV systems for agricultural applications, then there is a problem comes. This CDB is not counts. if voltage is more or C is more, right? Why C will be more? You are having a more configurations, again. So more panels are coming in series, then more voltage. When more voltage, and another side, what we are doing is that we are operating these devices at very faster rate. Right? Let us take your design a boost converter or buck converter or inverter. What is our ultimate aim? Like, you need to make your system is so compact, yes or no? And you want to make your system is so compact and economical and efficient, all these things. How you will achieve these things? How will you achieve these things? Let us take, I want to make my converter is so compact. You will take a buck converter. How can you make your buck converter is so compact? You can make your converter so compact by making your devices are operating at very faster rate. Right. So what happens is that we know that let us take buck or boost or whatever, a circuit and all these things, we are having these inductors and capacitors. So passive components are there. Like buck, we are having a switch, and then we have a diode, and then inductor, and then capacitor. If we take a boost, it will be like this. There is an inductor, and then there is means there is a inductor and capacitor. Right? Now, whatever configuration it is, even you take a voltage of some the output side of the memory, you have a LC filter to meet the voltage and current power qualities. Right? So when we are having these things, the main size and weight and volume is because of these passive components. Because you see that these switches are made up of it silicon or silicon carbide. They are lightweight. And your inductor is made up of inductor generally needs two things. What is inductor for? Like you see that N square by S. L is equal to N square by S. Inductor, if you want to design inductor, you need a number of turns and you need a permeability. This reluctance. Reluctance is coming from where? S is equal to L by mu A. L by mu A. Right. So you need to have some kind of a material which is having a permeability. That's what I said. Means this we are having, this we are coming with a core, this is coming with a conductor. Right. You take any kind of a core, you place it, like if you take any kind of a conductor, you place it on some kind of a core, this arrangement will give you the inductance. Because there is a number of turns of the conductor. Yes, is reluctance is not going to be all right. So physically it is having a length and then permeability. We need to have some kind of a ferromagnetic material which can offer that. So this arrangement, you see that this arrangement needs a core and a conductor. Conductor is made up of copper, your core is made up of Fe materials, right? So these are weight. Yes or no? So if your converter you are designing at a low frequency, let us say. I'm designing my converter with 1 kHz. In another case, I'm designing at 100 kHz. Which converter is weight and volume is very less. This case is you are having the weight and volume is very less. 100 times less. You see that what happens is that for the same XL is equal to what? 2 by F. If you can increase the F, 2 by F, right? If you increase the F, you can decrease the L. If I increase my frequency 100 times, the L value goes 100 times low for the same XL. Alright. So now my L value is getting decreased, means my N square base is getting decreased by 100 times. So my L value goes 100 times down, means now similarly capacitance also the same rule applies. Similarly, if you are using some kind of a topology, they are using some kind of a transformer. Transformer also you have studied 2-phase transformer, 6-phase transformer, size, weight, value, and even normal same concept is applied in case of a frequency transformers which are using power electronics. So all these things, weight will go down if you can go and operate at a higher frequencies. But this is very good. But this create a problem here. This create a problem here. What happens? This F is higher. This is giving advantages in our active mode. Right? So, but when F is high, what happens? This dt is very low. When dt is very, frequency is proportional to dt. If P is high, dt is low. If dt is too much low, because their frequency is too much high, then CdV by dt will be too much higher. Now, consider this case, in this case, 100 times more. That is what we are witnessing. Because of high switching frequencies, your this effect is more higher. One is that with operating voltage are more, right? In case of oscillating systems, your C is more depending upon the C and operating voltages. C is decided by the overall system capacity. That is more capacity generally. And then V operating voltage, more, it is more, and dt is decided by the switching frequency of our converter. Or we have decided that if you are going for high switching frequency, you will get advantages, but it is giving one drawback is here. Right. So it increases this current going to this mechanical body. We need to take that into account also, right? Because we are talking about this mechanical aspects, right? This mechanical body, right, is carrying this kind of current. Then if the CdV by dt is more, then what happens? This leakage current, ground current, passing through a mechanical element will create a problem to our customer in terms of a safety. Normally, you see that even your laptop computers, earlier days we are using a CPU. Right? Sometimes if you touch it, you would have feel that there is some kind of a shock. You know, they are operating at what voltage? 24 volts. Even you are feeling a shock. Now your systems are 400 volts or something, 800 volts or 1000 volts. So you get a more shock. And if this is more, then it will be more shocks. Are you getting it? That is a mechanical arrangement. Your chassis of your cabinet of your computer, if you are touching it, that cabinet, that you are getting a shock, right? Like that, the similar way you will get a shock if you are touching your mechanical body of your active voltage system. Right? So you need to take care of this, right? And we will see that. And then design compensation, like we need to take a mechanical strength and then height, intangible, durability, flexibility, right? So we'll see that how they will be affecting. Now with the help of simulation also we can see that. With the help of simulations I will show you how they will be able to affect the things. And as I told you that because of this arrangement, so the irradiation may vary. Sometimes if you place your panels like your mechanical arrangement is a flat or some inclination or vertical, different ways you are accommodating your PV panels, right? In that case, then what happens is that the net irradiation may change. Right? You are keeping your panels perpendicular to your sun, then it is always better. But the sun is moving. The sun is not fixed. If it is fixed, then always it is like perpendicular, then your panels will expose to maximum irradiation. But because of the sun movement, the panels will not experience a maximum irradiation, the maximum temperature. Whenever this radiation is changing, we have a relationship with power output to the G. G is a radiation, right? So like you are having less radiation, much less power. More radiation, if your panel is experiencing a more radiation from the sun, you will get a more output. You see that solar, in case of solar PV equation, if you see the current equation, IPV is equal to ISC into G by G naught into 1 plus alpha delta minus I naught to the power Vt upon eta Vt minus 1, right? So minus V PV by RSH. Right. We'll see that anyway. What I wanted to say is that your PV current is directly proportional to the radiation. So the basic equation of the PV. If the irradiation is now decreased, the PV current is decreased. When PV current is decreased, PV power will be decreased. That's what I read. P is directly proportional to G. Right. So means whenever you are making your mechanical arrangement such a way that you will get a maximum radiation throughout the day, your arrangement should be exposed. Then you will get a maximum good power, good amount of power you can collect from the sun. Another effect is that your temperature is also affecting your output. But temperature is having a negative effect. We'll also see with the help of these things, with the help of MATLAB. MATLAB. The tools like MATLAB, see this equation is like, it is not easy to solve by hand and paper. Right, it is a transcendental equations. Right, whenever there is a transcendental equations, we have studied numerical methods, right, to solve such kind of equations. So you need to do a lot of iterations to get your accurate solution. Right, but when we are having now, we are having very good processors. They are capable of installing very big software. These softwares are will be helpful for us to solve such kind of equations. That's where these, if you should get exposed and have a good experience with tools like MATLAB, that will be too much helpful to solving the system, right? Such kind of systems like degree voltaics, we have a lot of nonlinear equations. Even PV equation is like this. Like the complete equation is having a lot of nonlinear peaks will be there, so that if you learn some kind of software like MATLAB, most of the industries they have adopted MATLAB as a tool to solve their engineering problems. More than 80% of the companies, you go to any company, if you are working in R&D in power transformer, power system, or renewable energy, or electric vehicle, you will no doubt you will have to work on MATLAB if you are working in R&D. Right? Not only electrical like this, electronics, mechanical, like all, you see that MATLAB is having various toolboxes for dedicatedly designed for various fields of experts. So MATLAB is a very good tool, so that's why we are depending on MATLAB to solve our complete system. We'll solve things with MATLAB, so that how to implement also we'll see that. Alright, and then like angular instance, like previously you can see that the shading is also having effect. Right? If you're having some kind of a shading on your panel, so you will not get a maximum. Your panel will not experience a maximum radiation, then it creates some kind of a problem. Similarly, you are having some kind of a dust or something like that on your panel. Your panel will not be able to produce a good amount of output. Right. So actually, what happens is that like you have generally you have designed a solar water pump. Right. You have in your field you have placed your PV modules. Right? You need to have at least periodical maintenance. You need to clean your PV modules or something like that. Otherwise, there will be dust will be accumulated on your PV modules. Then your PV cells will not be exposed to the temperature, maximum irradiation or temperature available on the environment. Then what happens is that your pump is needing more power, but your PV is unable to produce that much. Right. So there will be stresses will be there. Right? So you need to take care. That's why always we need to have some kind of a periodic maintenance to your panels. You need to take care when you are designing inside the field, like because we place the in case of as I told you that in agricultural land it is like very harsh environment conditions will be there. Then the more possibility that your panels will get dirty. So at least you need to have a periodic maintenance. You need to take care. Want to take care when they are installing in case of agriculture for all. Alright, so like when we are having, as I told you that when we are having like more number of PV modules, you need to place. See, we are placing these photovoltaics for various purposes, which we will discuss shortly in case of your fields. Whenever you are placing, whenever you are designing such systems, so you need to have various things you need to take into the mind to get a good output, good yielding into your things. So everything plays a vital role, like the land width, solar production, supporting structure, inclination angle. This, as I told you, that this is the tilt angle. So the inclination angle. Basically, you need to select based upon your geographical location. You need to, this angle is not fixed to every place, right? So you need to optimize it to get a maximum output throughout the day, right? And you are, when you are keeping your system in the field, you need to take care of various loadings will be there on your mechanical arrangements. It is now exposed to the various winds, snow loads, earthquake resistance. You should have this mechanical body, whatever you are keeping, and medial have a very good and 90 system. Right. So you need to take a very good support. Means you need to design a very good mechanical structure to place your modules inside the formula. And then height and design we have discussed, and then usability. Whatever modules, generally PV modules, if you see the manufacturers, they will give you at least 20 years warranty. And like 15 years to 20 years, they are very reliable. That means that they are, but you cannot give a warranty to your power line products that much. Have you ever seen you buying a UPS to your home? Have you ever seen that you will get a warranty of 5 years or 10 years? Because of power lamp are not that much reliable like these PV cells, PV modules. Because I see that we have discussed here also. So in power plant converters, we are using some kind of switches and connectors and capacitors. Among all, the weakest element is the capacitor. The weakest, like if you compare MOSFET, diode, inductor, and capacitor, right? To generally we need to have the basic connectors, right? So among these four, less reliable is the capacitance. Capacitors, they are very failure rate is very high in case of a capacitor compared to other. So if you wanted to give a good life, and after we'll see that there is some topologies for exclusively for AV voltage. We see that in that we need to select a inverter with a low stresses on the capacitor. Means the voltage stresses should be very low compared to the other case. Then only we will be able to give a good reliability to the customers. Right? So, and then you have a good flexibility. So various countries there is some kind of arrangement they are following it. And there is a flexible photovoltaic systems also there, like in Germany. Even like in India, like compared to normal photovoltaic, these flexible photovoltaic they are costly. They are too much cost. Like yesterday one company was asking consultancy, they are asking that they wanted to make a solar water pumping of to produce 200 liters per minute. They want a solution, but within only 20 cases. Right. They want to have a flow rate of 200 liters per minute, and with a static head of 20 meters. They need to have a solution within less than 20 cases. Right. If you see that one PV module, their weight is like, have you seen any time solar PV modules like you see the weight of that? You see that 20 kg, 30 kg, the one PV module. Right? So, but nowadays actually they are asking for specifically for the place like Jharkhand and Chhattisgarh. There are a lot of farmers, they face a lot of issues. Right. If they are keeping this solution at their location, farming land, what happens is that someone is stealing. Right. If you keep your panels in your farming land and night someone steals, right, then there is a problem. That's why they are looking for a solution. If someone is really able to provide, I can give you the company details also. They are working in Delhi. So they were asking that they want a solution that solar water pumping within less than 20 kg. The weight of the system should be less than. How it is possible? Like we need to have a flexible. Nowadays, different solar PV cells are coming, right? But they don't care about the cost. Even normal PV solar water pumping of 1 HP is costing like 40,000. Even if it's like 1 lakh, that is fine. But they want a solution that should be portable and we should be able to carry by one person, one place to another place. Next, places like remote locations, they need such kind of solution. If someone is really making such kind of solution, there is a huge market for that. Because actually countries like India, when we are placing these kind of systems inside some farming land, the security is a big issue. As I know, if you are placing your panels in some field, the night someone steals, who is responsible? Right. So the production is very less. Right? That's why if you can make a portable IV voltage, then there is a huge huge demand is there, you can easily carry. Like you have 20 1 HP water pump system. If you can make it like 20 kg, you can easily carry whenever you need. You will place them in your farming land and then you just use for your water pumping or any other application. Then you get the work done and then bring it back to your home. So that kind of things are possible with this flexi photovoltaics. They are somewhat lightweight and the cost is slightly higher than normal photovoltaics. Right. And then, so when we are talking about civil aspects also, you need to construct proper like civil construction you need to make to set up your solar PV system wherever you are going to install, right? Because you need to plan your system that it should sustain for 20 years at least. Right. Your PV module life is 20. That is like your rainwater or whatever converter you are making, it is only lasting for 10 years or 20 years, 5 years. Then you need to replace that and you will get. But your solution, like entire solution, you should use it for at least 20 years. So whatever you design, you should keep it in mind that it should last for at least 20 years. Right? So, and then whatever arrangement you are making, you should have a long life, right? At least the arrangement you should make it for at least 20 years minimum, right? If you can make it more, that is better. But more life if you are giving, you need to think about the cost also, right? So if you want more life, you need to select things which can give it for more life. That's somewhat costly, right? But we need to take a trade-off always. Right? One thing is that we wanted to have. Like being a designer, always we want good reliability, efficiency, cost, weight, and then volume, compactness, robustness, right? So all these things, you want everything you cannot achieve in one place, right? If that is possible, you don't have much configurations. That is like even you are having a small PV cells. There are different PV cells are there. Monocrystalline, polycrystalline, different chemistry is there inside that, and then different cells are coming to the market with different performance parameters. Right? Even like power line converters or motors or whatever you are taking, a civil construction or mechanical arrangement, whatever you take, you need to always have some kind of a trade-off based upon your requirements. Right? So always you need to see that research basically mother is necessity is a mother of invention. Yes, sir. Whenever we are making some kind of a solution, first there should be some kind of a necessity. If there is no necessity, you are inventing something, how we utilize it. So first you need to see the necessity, what is the necessity. And basically that actually decides your driving factors. Let us say I design a inverter for UPS application. The same inverter you are designed for EV application. The same inverter you are designed for solar application. The same inverter you are designed for VFD application, variable frequency approach. Some other application. All the cases it is doing same task. What is the task? DC phase. It is only converting DC to AC. But why the task is different? Because the driving factors are different. In one case, in case of a solar, let's take a solar. Solar case, my driving factor, you should keep it in mind, should have a very good efficiency and then cost should be low. These two you should keep it in mind. Whatever solution you are making for this solar, you should keep it in mind for this. Your solution must offer a very good efficiency and your solution must be of low cost. Because I told you already, like countries like India and our customers now in this case is the farmers. They are very much cost sensitive. And second thing is that your solar PV modules, they are less efficient. Have you seen that the PV modules performance efficiency in the range of like 20 to 25, not more than that. Right. Typically 19 to 21 actually. If you see that PV modules, if you buy it, if you see the data sheets, in the range of like 19 to 21. Maximum you can get 25 if you are investing more. Right? So if your converter the remaining arrangement is also like less efficient than at the output you will get a very low output. That's right now. So if you can make these like whatever arrangement after PV modules if you are making with a highly efficient, then you will have a more output that can serve your purpose more better. Right? So like that, another side if you take EV, right? In case of EV, these two are not my major driving factors. In case of EV, major driving factor is weight and value. Right? Weight and value. So why this weight and value is more major driving factor in case of EV? The same converter. Now we have changed the design consideration. Right? What is our design consideration there? It is a less space, right? We have whatever setup we are making, it is having a limited space. Now we are designing for agrivoltaics. In case of agrivoltaics, you can keep you have a big land, you can keep your solution inside your land. Right. But in case of EV, you have a limited space inside your vehicle, inside your chassis. Right. You have a very limited space, so you need to have a good solution with a less weight and more compactness. Right? There you need to design a converter solutions with a less weight and less value. And another thing is that why we say that weight means if the power electrons converter's weight is increased, the converters where you will place inside your electric vehicle, inside your vehicle. If vehicle is that weight is increasing, if that weight of vehicle is increasing because of the solution, then what will happen? It is acting as a load, more weight, it has to draw more power to right, given mobility. Yes or no? So means you if your weight is increasing, then it is again drawing a more power from more your battery is getting draining faster. Right? That is the problem. Right? That's what I say that whatever we discuss in case of this agrivoltaic, we need means based upon the market segment to segment, the things are getting changed. In EV, things are different. In agrivoltaic, things are different. So we need to have a solution like this. So in case of agrivoltaic, we need to have our main first priority is that whatever mechanical or electrical or civil things you are designing for your agrivoltaic, you should keep in mind that you will get a good efficiency is the first priority. And second priority is that cost, it should be an economical solution. And then we should think about lifetime. Then next drive is lifetime. You need to have a very good life. Otherwise, who will buy it? Like if it is a less impact, sorry, less your solution is of giving a less warranty. If someone is giving you a warranty of 5 years and some other product of the same cost is giving a warranty of 3 years, which you will prefer? Of course, we will prefer having a good life, right? Warranty, right? So we need to have such kind of a right? Alright. So, right. So like this now in agrivoltaic there is a various kind of arrangements, right? Vertical mounts are there, reinforced regular mounts, right? So and tracker tilt mount is there, and also there is this PV modules also we are having a mechanical tracking, right? Like like the way the sunflower is rotates with the sun. You can make your mechanical arrangement also like moving with respect to the direction of your sun. Then you will your agrivoltaic system is exposed to more irradiation and temperature. When it is exposed to more irradiation, then your power is more. We have seen that the relationship between the current and then irradiation, similarly current and power. So we get a more power. So like this, there is various arrangements are there. So see that there are various nowadays actually we are making a lot of battery powered tools for even cultivation for farming application. See that there is a lot of tools which there are a lot of companies they are working, they are making agricultural tools, the battery powered. Right? So when you are having a battery powered tools, then what you can do is you can charge your battery with your PV modules which you are using in this field. So the PV, if the PV system, what we are discovering that if it is able to produce a constant voltage in this power by converter, then that constant voltage, right? Let us take your example 24 volts respective system, and you are having your agricultural tools, various tools which you are using for your agricultural purpose. They are using a 24 volt battery. Then you can charge that agricultural tools with the solar PV output which you are getting inside your field. Yes or no? So we can do that like that. There's a lot of companies, they are working on it. They are making a 24 volts or 40 volt standard voltage rated agricultural tools. I think battery power tools. Right? So like this, you can also think of it. And then actually I told you that there is in USA there is a NREL is a very good research organization. Like India we have CPRIs, IITs and IITs, like the previous institute for research. Like that NREL, they do a lot of research and then they do a lot of even agrivoltaics also they have done a lot of research and then they found that the agrivoltaics is making a more easy compared to the conventional agricultural system. Right. Alright, so now we'll see that some case studies of agricultural photovoltaic systems. In India also, as I told you that the government of India, in collaboration with Germany government, they have installed several agrivoltaic systems. In that, we'll take one system as a case study and that we will simulate with the help of MATLAB. Okay, let me show you some case studies if someone is doing some kind of a research on this agricultural systems. So there is a, as I told you, the government of India and government of Germany, they have come together and they have done some productive research in case of this agrivoltaic. There is different locations. You see that in Gujarat, Amal, there is a place, they have installed 1 megawatt system. Like that, I will just give you, just giving a glimpse about various agrivoltaic systems which was implemented in India. Okay, just I will give you a brief idea and then we will go to the simulation and we will see that how we can make one case study with the help of MATLAB. Okay, so these are actually on the side the pictures of that, and then like there is a next project is like 1 megawatt in Gujarat, Sikka, there is an area called Sikka. They have made 1 megawatt system, right? This agrivoltaics. So, so this is the site. On the site there is the forest, and then like this is like 100 kilowatt system, right? So you can see that here the location and the rating and when they are installed, when they are commissioned, everything I have given here. So I can share it with you. You can go ahead if you want. If you can see some kind of a case study for what the project details, basic product details are available. This is all research they have done it for agricultural systems. So and then. This is UP Noida, IIT University is there. They have also done some agrivoltaic system. They have installed the rating of 10 kilowatt. So who is the owner and what the maintenance they are doing, who is the scientific partner, everything. Like the basic details about the process. And what crops they are doing for the photograph is the master. And what crops for what crops they are using this agrivoltaic system. That all is and so you can see that there is this kind of a structure. Right. So here they are doing some kind of a farming. This kind of a mechanical system. There is a conveyor system of 10 kilowatt. They are using to cultivate the potatoes and maize and vegetables. Right. So it is in another place like they are using Allahabad University is there, Agriculture University in Agra. So they have also used this 200. They have installed 200 kilowatt system for this agricultural purpose. This is done by DSC to the DST. There is one scheme like here in the morning, Dr. The government of India has invested a lot of money. These all projects which are shown, it is done through government of India money only. Right, and the various schemes. Like there is one scheme called Mission Innovation. By DST, they have invested a huge stores. They have given to do the research, like the proposals which we make, which DevOps are made for this DP, like that. There is a R&D projects also there, right, where we can apply, and they have given a huge funding. You see that it's in 200 kilowatt, and earlier we have seen 1 megawatt. 1 megawatt is now like it's 5 crores, even to install, right? If you wanted to buy all the things, at least for one per unit, you see it is 50 rupees, 40 to 50 rupees, depending upon the quality which you take. Right? So you see that it is crores of rupees. Why each product is? These are not like private money, it is a public funded money. And for the project which I am showing here, it is done through some kind of a Department of Science and Technology, some another schemes through which government of India sponsored to promote agrivoltaics, which I am just emphasizing here, and they are presenting here. And for the crops, which crops they are doing here, I mentioned. Grams, brinjal, tomato, beans, spinach, and cauliflower, carrot, and gram. For that, they made this project. They have written this project. They wanted to install. They wanted to make a agrivoltaic system to farming these crops like that. Like so, this is the on-field photo. Like they did the system. Right? And another one is that there is another university. You see that there is like agriculture university in Gujarat. There is a place called Junagadh. They have also like there is also like a government funded project. It is like research funding. You can see the finance structure is like research funding. That's what I said. Whatever I am showing here is mostly they are they got a funding from the government of India to do this agriculture research. Right? Like this, there is a lot of projects there in the field of agrivoltaics are there. But through various schemes, see that Gujarat Solar Policy, finance tax they are following it, and then the project developer is that Clean Energy Limited. This is Gujarat government company. See the these are the things. Like that, there are various schemes. Just you can go through this document. I will share it if you are interested in what kind of projects the government of India is carried out in the field of agriculture. Right? Now, again, we'll see that how you can make one kind of solar water pumping. Even in Telangana, there different locations. There different projects are there. Here, one project I have taken for our consideration, and then we have made the solar water pumping. Okay, I will share you the product details. You can see that. For that, we have made the solar PV water pumping. Right? So this now we will take this case study. Right. So now you wanted to, as I told you that in the morning we have various models, but why we are selected as we have discussed. Now we have, I hope you are already familiar with the matter, and then this one we have done with the help of sim scale. Under the sim scale, there is a pickle library, and then there's a more library called specialized sim power system. Right, specialized power system library is there. Earlier version they used to call sim power systems library. Now they are calling in recent versions specialized power systems library. There, under that, we have the electrical components. Like we want a motor. We wanted to make the solar water pumping. So we need a induction motor. Under the sub-library called specialized power system, there is a electrical machines. There, whatever machines you want, it will be there. From there, I have taken this induction machine. Alright. So, and what we need induction machine, and then we need DC converter. Right. And then before that, we need a DC to DC converter, and before that, we need a solar PV module. Right. So this solar PV module directly also available in the MATLAB. Otherwise, we have a basic equation from that also you can model it. Fine. So either approach you can follow. If you are doing some kind of a research on modeling of the PV source, then you can model it your one. Right? Otherwise, you can take directly from the solar PV arrays available with the MATLAB. After 2016 onwards, we are having. Earlier, you see in 2012 and 13, 14, somewhere, the solar PV arrays were not there in the library. That time, you know, we have no option, so you need to model, right? That time, we used to model, otherwise, you can also take your directly from the library, right? This is the solar PV modeling equations, which we will discuss in the afternoon. That afternoon session is more on the solar blocks, solar cells, modules, and inverters. Right? That is a topic. There we will discuss about the modeling. Just I will now I will just show you one case study that I will give you brief idea. So this is whatever the modeling equations which we are having for the solar PV. With the help of that, this is model solar PV model. Alright. So this is like IVPV is actually your solar PV basically is having a characteristics like whether it is a current source or voltage source. Solar PV current source. It is having, you see that the characteristics will be something like this, right? The characteristics will be something like this. It is having actually both the nature. Right. Although we consider it as like current source, but it also having a, you see that what is the nature of the current? Current source means it is a current is constant, voltage source means voltage is a constant. In this region, like voltage is almost constant, in this region the current is almost constant. Really, so where your operating point is, mostly your operating point is near to this knee point. If you see the power versus current, right? This is the current, this is the voltage, right? If you see that in this region, almost current is constant. In this region, almost voltage is a constant. Right? So, means depending upon, like you can use it like a voltage or current. But we prefer that your PV module in a current source because your operating point is more closer to our constant current set. Right? So, here we are having our operating point, that's why we model also here also with help of current source. But it is also having a constant voltage nature also. Right? Current source means irrespective of the loads, it should be able to deliver a constant current. The voltage source means irrespective of the load, it has to maintain a constant voltage. It has to provide a constant voltage. It is having, you see that in this region voltage is constant, in this region current is constant. So if you want, you can also PV model you can operate like a voltage source also. I wanted to mention that it is having about the characteristics, but our operating point is more close to the constant current source. So we treat that it is a constant current source. So you see that this is a constant current source. This is a solar PV modeling. Out of that, actually, we need to place this decoupling capacitor. That is very important. If you don't place that, there is a problem that you may lose the stability of overall system. What happens is that actually what happens is that this is the inductor, like you are placing a boost command. Why? What is this use of this capacitor I just mentioned? Right? If you assume that if you don't place this capacitor, what will happen? Your current, this current at the inductor, you need this type, right? If you see that this is the boost converter. When boost converter, what happens when the switch is on, electric is getting charged, and then when the switch is off, electric is on. So something like this, right? So this is the current nature of our boost converter. Right? So you see that actually we design the inductor with certain people. Right? If you say that capacitor output, say capacitor generally we will typically design to get less than 5% of the voltage ripple, and this inductor we typically design to get 10 to 15% of the current ripple. Right? So what happens is that you see this waveform is having a two parts. This waveform I can represent like this waveform plus this. If I sum these two, then I will get this waveform. I decompose this waveform into two parts. One is having a pure DC component, and another one is only having an AC component. That is a ripple component. Right? It is having a so actually what happens is that whenever you are designing the boost converter that you are coupling with your PV module, if you don't place this capacitor, your solar PV module has to provide both the component of the currents. Are you getting me? So you see that it has to provide this kind of a current. If you don't have it, this decoupling capacitor. If you place a decoupling capacitor, what it will do? This will provide this current and this will provide this PV module will provide this current. Now we are having, you see that the equation if you write here, this is IPV and this is your IC, right? And this is your actual IL, right? Your IL is equal to IPV plus IC. If IC is that, if IC will be this and IPV is this. Now your PV is able to, should be able to produce only constant nature. This doesn't have any, it is like what? It is like positive and negative, right? What is the average value of the current is 0. It is not, are you getting me? This is the positive, this is the average value of current is 0. It is not doing any active work. It is only providing a ripple component of the current, which is needed by your inductor. So if this is not there, your PV has to provide this plus this. Not only providing this, it is also providing AC component of the current, degrades the life of your whatever PV system you are designing, right? So that's why this plus this capacitor plays an important role to enhance the life of our PV modules. This capacitor value is not so big; it is in the form of like 1 to 10 microfarad. So by placing this, you can save life of your PV module. That is the role of this capacitor. Otherwise, you don't need to place. If you don't place, also things will work. But the thing is that you will get now your PV is stressed to provide AC component and as well as a DC component. PV modules have been designed to provide a DC component, not an AC component. Right? So when you ask to provide both, then you will be feeling more stress and it degrades the life of the system. Right? That is the role of this. That's why we have selected this. And this is a boost converter structure. You know, and this we have discussed also. This is the inductor, and this is the switch, control switch, and then this is your diode, and then this is your output side capacitor. This structure is your boost converter, to stepping up the voltage. That is the purpose. And another thing is that it also doing another work called MPPT tracking, right? So we have discussed earlier in the morning, right, the role of this converter, how we can get a MPPT, right? Now here you can use different MPPT techniques called tail climbing or PNO or incremental connector, whatever. Right, you have a lot of MPPT techniques are there. You can use any one of the technique that will provide actually duty. I will show you that what is there inside. Okay, this is the PV voltage and current we are giving. This I am giving a sum of. This is the PWM modulator. It is MPPT algorithm. What you need to do, the basic idea in case of MPPT tracking is this. We are saying is power versus current or voltage. Right? So what happens is that in pattern and observations, what happens is that first we are at somewhere, and it is at some load and some irradiation temperature. Right? What we will do, we have this operating point. Now we'll just pattern, means we will give a small change in the duty ratio. Right? We'll now D plus delta D we are giving. Now D plus delta D we will give it, and then what will happen? It will move. Right? Now you are finding a new point. You need to find out the difference between these two. Difference between these two. Right? Because there is some difference is there. That means that we understand that it is not a maximum power. Right? Only you see that at this only we are having a maximum power. At this maximum power, you see that the difference between these 2 points is 0. dP is 0. Okay. What happens that it will, there is a difference is that means that it is not a maximum power, so we need to increase it. If it is another side, we need to decrease or increase the duty ratio. Are you getting me? So now it will again change with the same delta D. Now again it will find, and still it is not here like this, it will move. Once it comes here, now delta P, again if you are calculating delta P, now it is becoming, now hold that. Now keep providing the duty ratio only. Till whenever there is some change in temperature and radiation, what will happen? This operating characteristics will be changed. At constant temperature and radiation I was telling. So if temperature and radiation is getting, now it will move from, let us take radiation change. Now operating characteristics are different. Now here, now this is the not maximum power point. Now it will change the duty ratio and it will go here. With some iterations. considering the voltage change and current change, because of that power change will come, the power change is positive or negative or zero. If it is a zero, then we hold to that point, otherwise we will again change the duty ratio. So that is the key idea in case of fish clamping. This means that it is clamping like a hill. That's why they gave a name, hill clamp or perturbation observation. What we are doing, we are giving some perturbations in duty ratio and we are observing that delta T is zero or not. That's why they gave a name like that. And let us take another problem, and this incremental conductance. And so what happens in incremental conductance? We need to check the condition is that here it is a zero, right? Power is zero here, right? So what we need to do, we need to check that dI by dV is equal minus IPV or not. What is the power? Power is equal voltage into current. Right? So you need to differentiate dP. Then what you will get? V into dI and then I into dV. Difference is now u into v. U dp plus v into. And we know that at maximum power dp is equal to 0. That dp is equal to 0 at MVP. Then this is equal to vdi plus idv. Di by dv, this dy is bringing this side and then this minus v is bringing this side. Di by dv is equal to minus idv. That is what I have. This logic is employed in case of incremental conductance. Hybrid is conductance, right? So changing conductance is from the standard conductance or not. That is what they are checking. And that is happening stop there, and that is your operating point. That is how you are picking algorithm will be, and to consider your converter. Then that is how it will pick the duty ratio to get the maximum power at that operating point. Alright? So like that, whatever different algorithms you are having in the lectures, we can employ in. But industry wise I am talking, in industry mostly they use first method. And some industry they follow incremental conductance. Incremental conductance is more robust and more better in terms of performance, but it needs actually some very good processor. Like we are doing in the laptop, integration differences and all MATLAB, everything in the laptop, right? Because in the laptop we are having a general purpose processor that we say GPU, right? But in the field, we are having some microcontrollers of like 16 bit or 32 bit. Right? Here we are having 64 with 3.2 gigahertz. Right? You see that for laptop specs you are seeing it. Right? We are having like i7, 10th generation, 9th generation, and 3.2 gigahertz processor. What does it mean? 3.2 gigahertz means, what does it mean? If you can do the calculations of 300 crores in 1 second. Right, in 320 crores. 3.2 giga means 3.2 into 10 power 9. Giga means 3.2 into 10 power 9. H means number of cycles per second. So it can generate, your processor clock will be able to generate 320 crores of cycles. You would have studied microcontrollers and microprocessors there. You would have seen that for addition you need this many machine cycles. For subtraction you need this many machine cycles. Are you getting it? That means like if you want to do the differentiation, right? So it is very, you need a more machine cycles actually, right? And normal processors, if you study the microcontrollers and all, you would have done would have done addition, subtraction, and basic division and multiplication. Multiplication is not somewhat complicated. Alright, you would have studied move, addition, subtraction, and little bit of addition and multiplication and division, right? But you never done integration and differentiation. Have you ever done? You have studied a microcontroller subject. This differentiation and integration is very tedious task on these microcontrollers. So you need to have a sophisticated, but the end we see that in the research we use a D-space or OpenLab or whatever, they are in lakhs of rupee product. But the end, if you see the product, let us take before this I worked in Germany in EV industry, we make onboard chargers for 4-axle vehicle. At the end, all these controllers should be implemented on 70 rupees chip. Understand? At the end, they use some DSP processor, that processor costing only $1. Right? Even in research, we are using 7 lakhs these days, or 10 lakhs, because we don't know the coding. If you know the coding, that is the beauty of embedded systems. Like if you know the coding, if you know how to implement this is a platform. At the end, company uses only 70 rupees rather than 7 lakhs processor. Are you getting me? So, yeah. So what I'm trying to say, whatever algorithms you are proposing, sometimes it is not feasible to implement it on real-time processors, real-time controllers, which will be on your product. Right. So you need to see that the algorithms or controller, whatever you are going to develop, that should be feasible to implement it on these microcontrollers, DSP or PD microcontrollers. And then that nowadays we are using this Texas Instruments, NVIDIA, they make these microcontrollers. Right? We need to think that these controller algorithms can be PD or motor controller, motor controller, whatever. So that should be feasible to implement on such processors. Right? These two are very popular. Either this 80% of the cases they use this, and 20% of the cases they use this. And this needs more sophisticated processor than this. Okay. Like this, so then we have MPPT and then we have basically a program model. Right. To drive the work model. Here we have that. Alright, so this is boost part, and then there is the inverter. You can see that. Okay, let me show you that we have Simscape library, and then Simscape electrical we have discussed, and then this specialized power systems. Right? Specialized power systems. In that I told you that we have taken from electrical machines. So here, electrical machines. So electrical machine is there. Or if you want to make a power inverter, then you want a power library, right? So here our whatever devices like diode, DTO, MOSFET, IGBT, whatever you want. As per our circuit, you drag and drop and connect it. But like that we have connected. And this is the inverter, right? This is the inverter. Just this is the measurements only, don't get confused. This is the inverter block. And these are measurements where I wanted to investigate different voltages, different currents, or switches, and 10 voltage, phase voltage, currents, all these things, switch voltage, all these things like that. So this inverter, you have seen that these 3 decks will be there for 3 phases, each deck can be for each phase. So this phase output here I'm getting, the midpoint is connected to the output. This midpoint is coming B phase, this midpoint is connected to C phase, right? This ABC phase which are getting from the inverter that we are giving it to the motor. Alright. So this is the motor. And then now actually the control is a base of higher load. First thing is that the design of this complex. We have taken some value of capacitances and inductances. So that is the one side, and another side is that the control. With the two aspects, one should have a very good idea. One is the design aspect, and second one is the control aspect. So here we are designing a water pump, right? So solar water pump. So what you want is you need to have solar and then decoupling capacitor and then your converter. Alright, so here we are having a DC link and then we have this is a induction machine. This induction machine you wanted to control its speed to get a required flow rate. First I can like this we have discussed more than letters from minute. That is your record. So actually is it really happening at that or not? You need to check. You need to make a closed loop system. You know that in closed loop system the structure is something like this. We have some reference, right? So we have reference, we have a plant. This plant you wanted to have some kind of output. That output is as per our reference or not. We need to check it. If there is some kind of error is there, that error should be minimized so that we have some kind of a control. P development. So the controller, and then the controller will act given to actuator. Here in power plant is a modulator PWM. Right? So there is actuator, and then there is fan. So now this is the closed loop control system block diagram which we have studied. The same thing we are applying it. Now we need to have, this is my reference. What is your flow rate? Desired flow rate. First, to get the desired flow rate, you need to have some speed on your machine. That speed you need to set here. And then this is the actual machine speed, you need to measure it. And then you need to find out the error between these two. And that error, now, you need to minimize it. And that is the role of the controller. Now here, now we are using induction machine. Induction machine, what is your objective? We are controlling your flow rate for our water pumping application. In induction machine, you have studied various speed control techniques are there. There are various speed control techniques we have studied. Right. You have, what are the various speed control techniques? VPIR. Right. So, any other? Alright, anyway, so we see that the basic equation of very easy to remember. We see the basic equation NR is equal to NS into 1 minus H. Right? So now actually your NR, I said that I want to control my speed. Speed can be controlled by either NS or S. This NR is a function of two parameters called NS and S. One is that NS is depending upon 120 R by P. So frequency control or pole generator. Okay? So these two techniques we have studied. And also this torque is equal to 180 by 2 pi ns into s into square r2 upon r2 square plus sx2 whole square. That formula is remember. So the torque is directly proportional to s e2 square r2 square, something like that. You see that? Okay. So if you, this e2 is directly proportional to voltage. Your e2 is depending upon rotor voltage is function of your e1. E1 is a function of your supply voltage. So voltage control is there, voltage control is there, frequency control is there, pole changing technique is there, three methods. Now, and this E2 directly we are controlling rotor EMF injection technique. And if you are changing this R2, rotor resistance control, these are the basic methods which we are having in terms of induction. And if you can control voltage and frequency both, we said that the way of technique is there. So this is another technique. This is another method. Right, these are all conventional methods. The problem with induction machine is the speed control. It is not good. The speed control is not good. Why it is not good? But now we made it good. Now we have a very good sophisticated solution. Now your induction machine speed control is also very smooth like your DC machines. Very good. These machines actually they are known for speed control. Why? The main reason is that the field and armature, you see that the field and armature they are decoupled. They are 90 degrees apart. What is the beauty? If they are 90 degrees apart, the beauty is that if any two quantities, two flexes, now actually how we get a torque? Torque is because of the interaction of the two field flexes. One is the armature flex and second one is the field flex. How do you get it? Torque is directly proportional to IF into IA into sin of something. Right? So what happens is that sin of delta, that delta is the angle between your field and armature. So if you can make delta is equal to 90 degrees, then what you will get? Sin 90 is 1. So now your torque is directly proportional IF into IA only. In case of DC machine, you would have studied torque is directly proportional IF IA. In case of induction machine, torque is directly proportional rotor flex, rotor current, stator current, and then angle between these two. Are you getting me? This is like angle between these two is making some angle apart from 90 degrees. What happens is that if it is not 90 degrees, one will disturb another. One will disturb. If any two flexes are at 90 degrees, one flex will not interfere with another, another one will not interfere with another one. Are you getting me? Why? Because the rule is that cos 90 is flex based upon cos of that. Are you getting me? So we need to have always the angle between these two flexes inside the machine that should be at 90 degrees. Then we are having a very good speed control or torque control. Now what we have done in case of now we have advanced control like field oriented control, direct torque control, vector control techniques we are having. What we are doing there? So there we are applying some kind of a transformations. We have studied car transformation. By using this, decoupled nature. Right. Your torque is now not like the torque is directly proposed two component of current. IDS and SQR. Fine. If you apply transformer like that, then you will understand. But I don't want to go into the deep of that. That is a different subject. What I wanted to say is that now your torque is also different. Directly you are making, which is very similar to our distribution. One component of current is affecting torque, another current is affecting something like that. We are making a very good. Are you getting my? So these two are at 90 degrees. These two currents are 90 degrees. Now we are getting a very smooth speed control. Like that, we can apply things. Otherwise, this is like this needs again a very good sophisticated controller. The problem is this kind of things. If you need to apply a transformation, you need to have. You would have studied there is a power transformation like matrix will be there 2 by 3 times of. Remember that one. Right, minus of 0 root 3 by 2 minus root 3 by 2 and then 1 by 2 1 by 1. This is the matrix, conversion matrix for or similarly cos theta sin theta something like that. There will be these you need to implement in your processor. That is very tedious task. You need to have a sophisticated. That's why in water pumping applications we need to go there that much detailed sophisticated speed control. Here what we are doing is that we are applying a VPI. What is the beauty of with conventional and VPF? The beauty is VPF is making your fluxes constant. What happens why fluxes constant? E is equal to 4.44 pi ft. That is the basic equation of the starter order. 4.44 pi ft. Right. So T is the number of once it is designed, it is a fixed. 4.44 is also fixed. So E is directly proportional pi into F. So pi is directly proportional to E by F. LES EMF is directly proportional to supply voltage, so V is equal to pi is directly proportional. So once you are making this resistance constant, you can keep this fluxes constant. If you are applying voltage control alone, what happens is that you see that this is like if you are changing the voltage for particular torque, your speed is changing because your S is changing. Are you getting on? When S is changing, your voltage is changing, your speed is changing. But the problem here, when voltage is changing, your flux is changing. Right? We are only applying the voltage. Similarly, if you are changing the frequency, of course your NS is changing. Your NS is changing, NR is changing, your speed control is happening. But at the same time, your flux is getting disturbed. This flux is getting disturbed, it may oversaturate, may saturate your machine, or it is not able to produce a sufficient amount of the flux to get your desired torque. That is another problem. That's why we don't prefer independent voltage controller, independent frequency. Anyway, frequency control is tedious task because we are having constant frequency. You need to vary. If you want to get a variable frequency, you need to have cyclothermal or something like that. Right? How we can vary the frequency? It's some problem. Voltage control is easy. That is what you are using in fan regulators. Fan regular what is doing? It is a triad. Anti-parallel combination to that specific like that. So you are varying your voltage. This application doesn't need this much sophisticated. That's why we are using that. In this fan control. And what we like we need to make your constant with different environment. Your environmental conditions are keep on changing, right? Morning to evening temperature conditions keep on changing, but you need to get different things. So that's why the best method, if you see that in all the fields, if you see that water pumping application, they are using VFDs, variable frequency transfer. VFDs. What variable voltage or variable frequency. But some companies they will say like VFD, but they don't really provide variable voltage and variable frequency. Simply they again do voltage control frequency, not both. Maintaining the range of the tedious task in real time. In MATLAB it is easy, somewhat. But now the same thing you need to implement on microcontroller or DSP. Now you need to code it. When you are doing a coding for simple thing, you will face a lot of issues. Lot of things you need to take into account. You need to go to the register level. You need to play to the registers. You are having 32-bit register. Each bit is doing some specific task. So the same bit is doing multiple tasks. You need to configure them properly. You need to understand registers properly. Then you need to configure properly, and you need to get your desired task. And everything, your logic should be implemented on digital level. Not like BI means KB plus K base. In MATLAB, you are writing KB plus K base. But in real life, that is not valid. Now you need to implement that in terms of your digital logic. Right? So one of the free in a way we are using this key by up. So it will set your frequency and the same proportion you need to change this frequency will change the voltage so that you will get V of resistance constant, then you will get a reference voltage, then the reference signals will give it to the modulator will input to the gate signals. Like this, there is a basic idea, that is what we have done here, you see that. Alright, there is a speed and sensing, this is my reference speed that I have given to the component that the generating a frequency, this is the frequency. The frequency inside that you can see it. Alright, the frequency to voltage. This is the frequency which we got it from our PA controller, that is what we have discussed here. The frequency, and then we are in the same proportion, we are generating the voltage, and both these two we are generating a Vm sin omega t, Vm sin omega t plus 140 or 240. That is how we generate reference waves. Once these reference waves are generated, then you can apply reference PWM like that harmonic, sinusoidal. Here I am talking about sinusoidal, then harmonic, space vector, right? Different space vector, whatever you want, you can apply. And then you are comparing with the carrier wave, then you will get a PWM pulses, and the PWM pulses you are giving it to. You see that the PWM pulses which are generating here, then I am giving inside this block. Right? So once you are doing this, then you will get. If everything is covered, everything is now. If you open everything, there is some particular value. As I told you, right? When you are clicking it, you see that every value is having its own meaning. Right? We need to know the design aspect. When you are doing a power plant stuff, then you will understand the design, and then this every block you see that is having its own values. Right? So they like the anti-wind control this thing is there. But what I wanted to say is that your KPK or thing, you need to know that how to design. Once you set particular values, only you will get your design performance. Are you getting me now? Alright, so alright, this is actually with physical components. Similarly, here I have done modeling also. That you can also model your induction machine. We have studied machine model. Induction machines can be modeled on different frame theories. We have studied 4 different frame theories like arbitrary rotating reference frames, synchronously rotating reference frame, stationary reference frame, and rotor reference frame. You can use any reference frame theory to model your induction machine and then object ensemble. Anyway, that I am not touching on. So you see that this is my theory, and then you see that. So you see here. So whatever this one is this. You see that there is 2 waveforms you can witness. One is that blue and one is that yellow. One is that it is producing your reference speed, and second one is the machine speed. See that our actually it is spiking. Whatever speed, the speed is now actually not a constant. You see that? Have you seen that the speed is not a constant? Speed is also a function of pump flow. We are using a pump flow. Are you getting me? The like not a constant reference are not given. Here it is generating a torque is directly proportional to. If you take a fan speed, what is the torque? There is a relation, right? Torque is directly proportional to omega square. Directly what are pumps we have taken? Centrifugal pump. That I have taken an equation and then I have modeled. That is how it is generating my reference, and then my machine is also able to produce the same speed what you are asking to get at the maximum power. Are you getting that? So you see that this is the load torque. Whenever the load, even I am changing my load torque, the yellow is my machine torque is able to produce the different. Here I have introduced my at 2 seconds. You see that I have changed my load. Okay, so you can see it in my. At the instant of 2, see that. 2 seconds I have changed 26.67 Newton meter to 20 Newton meter. But still, when under that condition, whatever speed you are asking, it is able to produce. Or you can vary your speed or whatever according to the able to produce. Okay. So like this, you can make your water pump. next thing we will discuss in the next session. Maybe now time we are already running over time. Alright, so thank you.
Thank you, sir, for explaining the civil and mechanical aspects of PV systems. Now, participants are requested to assemble in the department. Okay, after lunch, all of you assemble here already. Second sessions are also starts here itself. Okay, thank you.
Thank you, sir. Thank you for spending your valuable time. नहीं कहा हाँ हाँ वो नहीं मिला ना मैं नहीं है ना मैं छुट्टी में है ना आज हाँ इसीलिए वो आप व्हाट्सअप हाँ थोड़ा प्रवीण जी को बोल दीजिए व्हाट्सअप करने के लिए व्हाट्सअप करना फैन आपके पास लग दीजिए
రన్నింగ్ లో ఉంటుంది కదా
अच्छा उसके लिए मैं कॉल किया था नहीं वो नहीं ठीक है रवि जी वो नहीं है ये ये तो हो रहा है ठीक है आने के बाद थोड़ा मेल कर दीजिए मेरे काउंटर है
అదే కామెంట్స్ ఇచ్చేస్తాను ఒకసారి చూసి
ఇడిగైతే డల్ లేదు నేను స్క్రీన్ కనెక్ట్ చేసిన తర్వాత
కొద్దిసేపు అయ్యాక ఇది కూడా ఆన్లైన్. Okay, good afternoon. We start our session now. Inverters, solar cells, modules, and applications. So in this session, now in the morning session, we have agriculture, what type applications. We have seen about water pumping. Right? So now actually we see that in this, let us take in this application, so this inverter plays a vital role to get about this performance. Now, even not only this agri workers, also this FTP is also having another aspect called EVs, right? So now actually whatever inverters we are discussing now, that inverters, there are a lot of approaches available and how they have been emerged, why they have been emerged, and then we'll see that with respect to timeline and what is the improvement they made and how the pulses got evolved. Okay. From the beginning we'll see it. So, and then we'll see sort of topologies in the singling term. Like whatever topologies we'll discuss. Some topologies, like I will cover almost 45 different topologies. How they have been emerged, why they have been emerged, even though there is topologies are there. And they are inventing some new topology. First of all, we need to criticize the existing topologies, right? Then only then they will get some scope to publish, right? So how they are published, see that. And also, what are the trends are there in another industry? We'll see that. As I know that, like solar cells, as a basic element, we'll see that solar cells and basic element will go to our idea of these are the modules and we go to models. As we see that the solar these are representation and this is actually we see that PV cell is a basic element, right, which can convert solar into electrical energy. The electrical energy is how we need to see that how this solar energy is converted into electrical energy with the help of this photovoltaic cell. Photovoltaic is a basic element which can convert this solar into electrical energy. The input is solar and the output is electrical. I see that like conventionally we have seen in even in the morning, like we have discussed about the characteristics of the solar PV cell. Right? Solar PV cell characteristics it is like although we are treating like it is a current source, it is also having a nature of voltage source also. We have discussed, but most of the time our operating point like on the side of current source. So we are taking the current source. Right? These are characteristics I have done also in the morning. These are the characteristics of the solar PV cell, and with respect to radiation, how these things are getting changed. When we are designing the things for solar applications, whatever we are designing, maybe water pump or any other application, we need to take care that irradiation and temperature gets ready. Right. So, what is the what is the range of irradiation and temperature you are considering that you need to take into account? Accordingly, your output of this PV solar module gets ready, right? And then you always need to satisfy the load demand. You need to see that how much input variations are there at your converter input, and then your converter has to produce the required parameters to the motor. Right? And in this, various configurations are there that we will target later. And typically, we see that typical IV characteristics is that generally we say that when you buy a solar PV module cell, we get the data sheet. The specifications will be mentioned on the data sheet. That data sheets, the characteristics they will be characterizing at standard test conditions. We say STC, standard test condition. Standard test condition means they are characterizing that at 25 degrees centigrade and 1000 watt per meter square. These are the standard test conditions. They will be the data sheet. That data sheet is not true all the time because your radiation temperature gets varying, right? So accordingly, the operating characteristics will be moving up and down, moving like that. So depending upon the operating conditions, the typical IV characteristics. And then in solar cell, there is a defined chemistry is involved, right? How we manufacture like silicon and compound silicon and organic semiconductor, right? Silicon semiconductor and compound semiconductor and organic semiconductor. Actually, these are all the chemistry people. They will do research with the different materials and chemistries to improve the performance. Performance of the software. So anyway, we are being electrical engineers. We have to place them. We will not change the chemistry, right? So we'll see that among all these things, whatever you see that whichever technology is having a measure efficiency, we will take them, we'll learn them, and then we'll utilize them in our application. Right? This is like single crystal solar PV cells will be like this, and polycrystal. By seeing that panel, by seeing that we can easily understand that like single crystals will be like this in the polycrystal. You see that the color will be different, right? By seeing that we can. And then you see that the different modules like single, as we have discussed, that single crystals, polycrystalline solar PV modules will be like this. And a module, they like 128 module, like 25 is the 6.5 and 4.8 VMP and IMP. This is for polycrystalline. You can see that 25 point some it is like 120 watt. Right. Like we know that cells, several connected cells, several cells, if you are connecting them in series or parallel, then the combination we say is a module. And several PV modules you are taking and then you are connecting them in series or parallel, then we say this combination we say is a cell module and right? Several cells, if you are connecting them in series or parallel, we get a module, and several modules we take and then we connect them in series or parallel, then we will get an array. Right? So it is like the hierarchy is like cell to module, module, array. Right? So and see that roughly the size of PV station, like typically thumb rule, like 1 kilowatt PV needs 10 meters square area. Typically, like one, there is a, like this generally when we design some kind of a solar PV, we take the sizing of the space. So there's some solar PVs are like integrated, like some houses, some house you are having a roof on the roof, where utilizing the space to install a solar PV module. Right? So, they like in Japan, they have installed and various solar PV systems. They have integrated for several applications. Now we'll talk. We have seen this, and then now we have seen that maximum. These are like IV characteristics. This we have seen, and then now PV characteristics. If you see it, and then this is the PV. To get this maximum power, we have discussed that here this load may vary, or temperature, radiation may vary. Accordingly, to maintain the maximum power, we need to have power conditioner. Power conditioner means conditioning the power to get maximum power at various temperature, radiation conditions, or at load condition. That we have seen mathematically also here in the morning. This will go. This is all we have discussed on the board. So anyway, this is about basics of solar PV cells and the modules, and I am not touching this MPPT. There are various MPPT techniques are there, and we will first discuss about the inverters. Right? So let me go to the inverters. Alright, so in this we'll discuss about solar PV conditioning units called inverters actually. Power conditioning, it condition the power, right? So one condition, one nature to another, right? And the review of existing solar PV inverters and the comparison of various topologies and which topology is suitable for what. Actually, being a designer, we need several performance parameters which we discussed here. So, which topology is giving you what? That we will see. So these are we have seen actually see that like when I was in USA we have designed a 200 kilowatt solar PV inverter. This is like 200 kilowatt hour inverter. You see this is the load RL load. So this is 200 kilowatt load, and this is like experimental results that 200 kilowatt even single module. I will show you the module will be like this. This is the inverter 200 kilowatt hour inverter almost small. Almost, you see that this is size is very small. And that is the beauty of this advanced materials. Like we have this is with silicon carbide devices. Silicon carbide devices they are offering a very high switching frequency, highly efficient, and the power handling capabilities are high. This is the advantage of wideband gap devices. So, and the efficiency is also too high. You see that there are different manufacturers' devices we have selected for the same 200 kilowatt. You see that. These are Rome is our manufacturer of this modules, micro semi and P and semicon we have compared. See that the semicon, these are all actually SiC devices. And actually our target is that first of all, before designing inverter, we need to select a proper devices, right? So inverter if you wanted to make, you need to have a proper devices. So now our target is that let us say you wanted to design 200 kilowatts. Okay? So 200 kilowatt, 200 kilowatt. Right? So at 200 kilowatt, this is your power handling capability you want to design. And this is at let us say 1000 volts. Right? Your DC bus is like in case of a solar, our DC bus is near to 800 to 1000. Right? So in that case, actually, what we will take a 1200 is a standard voltage of modules. If you want a module at 1100, you will not get it. If you want it at 600, you will get it. Some standard range you will get, right? Standard operating voltage you will get. Like 1000 you will not get it, and next one is like 1200 and 1700, something like that. You got it? So now actually for this you need to select like 1200. Let us say if you are designing at 1000 volts, you need to select more higher than that. Otherwise, if you are designing 1000 volts, if you are selecting 1000 volts, you will not have a medium because a lot of things will affect this. We'll see it together. So now let us take a design. Now, what is the current handling capability? One device is let us take 1000 volts means you need to have a 200 amp. 1000 volts and 200, then will give you 200 kilowatts. Right? So, but actually you should select more than this. That's why we have selected actually 300 amp. So we have selected 1200 volts. For this 1200 volts, this design we have selected 1200 volts and 300 ampere. That is how we select voltage and current rating. See that 1200 volts, 295, something like that. So if you are using this, we need to take two, we need to connect them in a parallel actually. Right. So we get 120 volts you are having, and you need 200 amperes. Right. You are having a reverse of 120. Then you need to connect two in parallel, and you will get 240. Like alright. So you see that now for all these devices we have calculated their switching losses, and then we have calculated their resistance. Right. So this green one, you see that this is with IGBT, right? This is with IGBT. This semicon IGBT. Remaining all are SiC MOSFETs. In case of MOSFETs, we have studied already in silicon, right? If you want a high power, this is very high power. 200 kilowatt is not a low power. Medium power, it is a high power. In high power, you will have only option with IGBTs. Yes or no? For high power, high voltage and high current, you are having IGBT. You never get a MOSFET which can handle this much voltage and this much current. And alright, so but with the advanced materials, we take a silicon carbide. Even with MOSFETs also you can handle this much. This is a MOSFET. This is a MOSFETs. Except last one. Right. So we have compared. You see that this silicon IGBT, right, is giving you around 93.4 efficiency. Right. So, but this silicon carbide is almost giving 99.3. So how much gap is there in efficiency? How much gap is there in efficiency? That is almost 5%. That is 6%, but we will take it for 5%. If you take a 5% of a 200 kilowatt system, right? 200 kilowatt solar PV system we are designing it. Now, if I take a approximate, I will get a 5% higher. Right? 200 kilowatt, 5% means how much? 5% of about 200 kilowatt. How much? So 200 kilowatt means 200 units. That is kilowatt 1 hour is 200 units you will get. Right? So now how much you will get? How many units you will get in a 10 units. That is take this much power. This much power you will not do it for home. This is for commercial applications only. Commercial applications, you know that 1 unit is like 8.5 rupees. Yes or no? So per hour you see that 850 rupees you are saving per hour. You understand? If I take normal one compared to that, since I am able to produce a more power, means I am saving 850 rupees in a 1 hour. In 1 day, how much? Into 24. Okay. So in 1 month, how much? 30. And right? And then now, 12 months. This much in a 1 year, you must save this much use. Profit. See that 850 to 24 and 13 to 12. How much? There is some lakhs, and it will come around 5-6 lakhs. Right. So, and that is for at least 4 years. You like you will get it 4-5 years. Right. So you see that 4 into 6 lakhs, 24 lakhs. We are saving. That much advantage you will get. You are having a good technology. 4 lakhs, 24 years. If you are able to save 24 lakhs, you are generating more revenue. Really, man, every year you are saving, you are generating like almost like a salary, 50,000 per month. Really, man. Oh, just like by selecting a proper technology. Nothing we are doing. We are investing in both the cases. Yes or no? But, that is how we can adapt a good technology so that we will have more revenue. Alright, so solar PV systems like we take solar PV inverters like solar PV systems, mostly 95% the systems are like grid connected and 5% the systems are like off grid, like standalone. Right? So whatever we design inverter, so actually off grid inverters are different, actually grid connected inverters are different, features are different. As we are told in the morning also, like depending upon the market segment things are getting different. Right? In case of a grid, actually what you need to do, you need to whatever inverter output voltage you are producing, right, that should be synchronized with the grid. So your reference is the grid, accordingly you need to produce the voltage and frequency, right? You phase angle, all these things you need to maintain, right? Grid conditions. And in case of standalone, you don't have all these things, so you can generate a sinusoidal or requirement. Okay, so that is how actually we will change the design for grid connected system. And then you see that in case of a solar PV, there are 2 ways you can actually get a power. The cameras. One is that we are having DC to DC converter and then DC to AC. Right? So actually what we have done is that we need actually higher voltage. Right? That is like you want a 400 volts. 415 volts, let us say. Right? This is the line to line voltage. This is a line to line RMS voltage. To get this, actually, you need a DC link at least greater than 650 volts. We are having 650 greater than that. That's why we will select 800 volts or 1000 I told you here. So this is because actually if you are having this much, then only you will be able to produce this much voltage. Because in case of inverters, we know that output voltage formula is MVDC by 2. Yes or no? If you have 800, then by 2, 400, 400 into 0.8, 320. 0.8125, 325. That is what actually you want. So you need to have at least that much higher voltage, depending upon the modulation. Okay? So that's why typically we will select a DC bus like that. It is in the range of 800 to 1000 volts. That is why I have selected. All right. So, so you need inverter input is this much because you are using inverter. That inverter is producing only m times V is equal to gain. Right? Are you getting me? So this now actually we will see some topologies that not stepping down. There is several topologies with high gain topologies like with transformer without transformer. There is several topologies. And one more, that is what we say that it is a single space and this is like two space. And actually, when we are doing it, this DC to DC and DC to AC, we need to maintain all these things in case of a solver, right? One is that MPPT tracking we need to take care. If we are using only one converter, that converter should be able to have all the features. MPPT, DC to AC converter and voltage. If you are having two converters in upper configuration, we say it is a two-stage power conditioning. Two-stage power conditioning. In that, actually what we will do, MPPT will incorporate in DC to DC and DC to AC and MPPT and voltage boosting is done through DC to DC converter and DC to AC converter is done through inverter. Right? But in single stage, everything has to be taken care by only one converter. That is more difficult to design. Alright, so we'll see. And in two stages, there is various ways you can achieve this. Two ways you can achieve this. Right? You need a sinusoidal voltage or input is a constant. Alright. So one way is that you can generate DC to DC like I have stepped up, and then we are using inverter to get a AC. Another way is that you see that here there is a DC, and here I can get a rectified sinusoidal. Rectified sinusoidal. Are you getting it? Simply I use a inverter here just to change the only off cycle. Are you getting it? This off cycle you need to reverse it. That's all. Here what is the beauty is that here which one is the better, this one or this one? This one here is inverter is operating at switching frequency, this one is operating at line frequency. So less switching losses here, more switching losses here. But here the problem is that when you are sizing here, you need to have a bigger rating of DC to DC converter. But in case of a DC, like let's say, if you are designing a converter, but actually your average values will be like this. You are having a waveform like this, but its average value you know it, right? 2 m by pi. This we have studied in case of 2 m by pi. So your peak value is higher than your average value. So in previous case, I need to design here the components, all these things for average values. But here I need to select for peak values. Peak value is higher than this. That's why here the values, whatever you are selecting the MOSFETs or IGBTs or inductor and capacitor, there you need to select it for a higher voltage current ratings. That is the problem. Alright. So what are the functions you should have? Whether it is a single stage or two stage, it is need to have a power conversion at the required voltage and frequency. Alright. So and output power quality should be, you should have a, you should be able to produce with required standards, like depending upon different countries you have a different standards. Whatever country you are designing it, you need to fulfill their requirements. Alright. So and then you need to have a proper isolation with your DC. Right. So if you are not having isolation, it is facing a problem. Right? So and then also you need to have MPPT and active power reactive power control, all these things. And you need to maintain a good power factor, good THD. You should not inject any DC offset current, voltage and frequency in the proper range, and islanding operation must be there. Reconnection, if there is some kind of fault is there, it should be able to detect and it should be able to protect your systems. And then on fault is there, it should be automatically reconnected back, and grounding should be there proper. All these things we need to have inside your inverter. Then only that inverter is the best. So you will see that which topologies are able to provide all these things. It's like that I told you that different countries follow different standards. India we are having following this. Right, within like if your voltage is less than 80%, you should be able to disconnect your system less than 22 seconds. Right. So I like that different USA follow different and Germany follow different and Australia. Harmonic we are following IEEE 519 standards. Right? So the flicker, DC injection, how much it should be there, frequency of within what range you wanted to operate. Right, if it is greater than 50.5, like you need to disconnect the things within 0.2 seconds. If it is less than 47.5, so disconnect in 0.2 seconds. All these things standards we need to fulfill when we are designing our inverter. We need to take care of these things. defined to provide all the features, right? So like that solar PV specs, their standards are mentioned here. Like if it is a PV module or crystalline type, they have to follow IEC 6125, IEC 615. These different standards. All right, different countries they are following. All right. Okay. So now we are talking specifically our silicon inverter. So we'll see that what are the manufacturers are there for the inverters, and you see that these are the main manufacturers who are selling their inverters in India. The SMA, right, and the ABB, Power Money would have had all these names. So among all these things, the SMA is which they say taking a more major step. Right? So these all you see that no company is coming. Right? So these are like European, US or Chinese. So, but that's why if you're doing research, if you can make a product, if you can product it, if you can make a product, and if you can sell it, it is having very good market. Because if someone is able to manufacture in India, then if someone is importing from China, you know that government of India has kept a lot of taxes on imports. Getting me? So if you are able to manufacture things here, then the import tax will be not there, the product cost will be much. Getting me? So there's a huge chances are there if someone is making inverter, then there is a huge scope to manufacture. And you see that what are the features we have discussed earlier, what different manufacturers are there, different features are there, or they are incorporating every feature or not. Things are there, products. That's what happens. Yeah. So most of the things they are taking care about harmonic induction, like harmonic proper harmonic control they are making, and then DC offset they are taking care of flicker control, anti-aligning, and reactive power support. Some companies they are not offering. LVRT, low voltage right and frequency regulation, they are not maintaining these four manufacturers. Right? So in case of solar PV inverter, when they are making these four different configurations are there called central configuration, and then string, multi-string, and then AC modules. So these are four architectures we are having in case of solar PV systems. Right? Central, string, multi-string, and AC module. We also say micro inverters. So what is the difference? Like here you see that all the modules are gets connected either series and parallel. We got a array, right? That entire solar PV having only single inverter. You see that, right? So here only there is only one inverter centralized. All the PV inverters are PV modules are connected, and then one connection will bring it to the inverter, and then inverter is connected to the DC. And the next one is that strings. Each string is having a dedicated DC to AC. You see that. There is a string, there is a string. Each string they are having a that's why there is a string. And then multi-string. Multi-string means each string having a DC-DC dedicated DC-DC converter. And then all this kind of configuration having a single inverter. Right? And then AC module means each module is having a DC-DC power. So what you observe, which one is the better? Which one will you prefer? In case of AC module, let us say if you talk AC module, each module, right, we will get in the market by not more than 78 volts. Right? We'll get like not more than one module will not get more than 78 volts. Module will get up to 500 watts power. So let us say you have a 70 watt DC and you need to get a 325 volts peak AC. So you need to have some kind of a topology which can be. So here actually in case of central, if you, on the other hand, we will come and discuss about central. In case central, you have a lot of PV modules up there. You can connect them in a series to get your desired voltage. You're having a lot of modules, right? You can connect them in a series. Each module is providing a 70. You want like 700, you can take 7. Right? Connect in a series, you will get a 70 and then you will come. Or you are having a 70 modules, you take 10 in a series and the rest you can in a parallel. Are you getting my not? To get your things. Right? That is how these things will vary and their advantages and disadvantages like that. Now we will see that the topology, there are several topologies invented, and why they have invented. We have discussed that these are the features we need to have. Some topology they dedicate for grid connector standalone. Some are very exclusively for grid connector. Some are only for standard. And then some topology they will offer you isolation. Isolation is one of the requirement, and then power decoupling, number of stages, dual grounding must be there for providing safety. Power handling capability should have good power handling capabilities. Not all converters are suitable for high power or low power. Some topologies are good for low power, and some topologies are for high power. So like that they have right? Size, weight, wide range of operation, tooling requirement is required or not, theoretical operation is there or not, filter requirements is required or not, control is complex or not. Right? So we'll investigate whatever I will discuss with respect to all these points. We'll investigate and we'll compare. Okay. So now all the topologies which we are discussing, either they will come in a multi-stage or two-stage or single. Right? So now first topology we discuss. This is the, see that I have simulated all the topics. I have, for your better understanding, I kept it in with the color coding, different color coding, and their different switching pulses and the input voltage, output voltage, the middle, wherever it is required, I kept all the results. So for better understanding, you can see that the same color coding they follow the same time of on. The green will go on one time, and then blue will be on at another time. The same way you cannot turn it on both at the same time, right? Otherwise, it will red short circuit and blast. So that I follow. You see that what happens? This is like how many stages are there? Multi stages, right? See that there is a DC to AC. This DC to AC is DC to high frequency AC, and then high frequency AC. We are stepping up with that of high frequency transformer. This transformer, what it will do? It will change the voltage. Right? And then this high frequency AC to DC. That DC we are converting into AC. There is a three stages are there. What is that? First one is DC to high frequency AC, then high frequency AC to the DC, DC to line frequency AC. That's why we say this is a multi-stage. More than two, we say it is a multi-stage. Two stages are there, two stages. We say this is only one stage, one stage. And then single stage, multi-stage, and dual-stage. Okay. All right. So you see that. That is the operation which I told you. Right. So first we will convert DC to frequency AC, and then transformer is stepping up the voltage to get a zero voltage level, and then that you will convert into the DC, and the DC will be converted back to the AC with the help of this DC. All right. And then this is the operation during positive half cycle, how this is operating, whatever negative half cycle, how it is operating, I kept the difference of course. You can see that whenever these two are on, what happens? This transformer is experiencing a positive voltage, that positive voltage here, the drivers will be on and they will get a DC voltage here. The DC we are converting with the help of these positive AC will get, positive cycle will get. And here negative half cycle, what will do? These two, blue one will be turning on and blue one will be turning on. This transformer is experiencing a negative voltage. That negative voltage will be amplified with the transformer. That amplified will be converted into DC with the help of DC2, and then the DC will be converted into negative AC. Right? So positive and negative like that. During positive cycle, what is the equivalent cycle? Now in this, as I said, we'll investigate all the features are there. What we want. So first one is.
I have a question.
Yes, sir.
So for the particular application, how you are able to select particular type of converter?
Yes, sir. So that we will discuss, sir. Actually, this topology is very good for wide voltage. Like at the last, sir. So, sir, actually, once we have done all the simulations and all the implementations done, then actually I compared all of this. So now, like what you want, accordingly, we need to select, sir. Like, so some topologies they are like single stage
some like whether, of course, if you see that single stage, dual stage, and three stage, among all these three, single stage is the best in terms of a compactness. So if you want a compact system, then you need to go for single stage. In single stage, now next thing is that you want to do it for grid connector or standalone. Once, let us take your fixed it, some topologies they are good for, their supports standalone, some topologies are they support grid connector. Once that is some topologies eliminated based upon that. And then we want a safety feature you want to incorporate, means you are having a dual down concept is or not, we need to check it. Then we need to see that, and if you want to upgrade it, if you wanted to get a good life, then you need to see that what kind of a capacitor they are using. Accordingly, we need to segregate and we need to select the topologies based upon various features. Once we have done all the things, then I compared all the topologies. Then based upon our requirement, like based upon our application, we need to select. Like let's see that. See, sir. So this we have discussed in the morning. Until depending upon our application. Let us take we wanted to have a PV inverter. Now we are trying out a PV inverter. Our driving force is that it should be of low cost. First priority is that these are the driving factors as per the applications. Like whenever you are designing an inverter or converter or any kind of a power electronic device, for this PV application, we should keep it in mind that first is that low cost and then high efficient. These two are the major driving. Once you achieve that, then you need to see that what is the life. Is it happening? Then weight and volume. Weight and volume is not a high priority. But now you see that the same inverter, we are let's say now we need to select an inverter for EV application. In EV application, our first priority must be compactness and lightweight. Now you need to select a topology such that which topology is a lightweight, which topology is of a small in size, compactness. And then we need to focus on cost and lifetime. And then we need to say about efficiency. Now if you have to go for the wind application, so first priority is the efficiency and then cost and then reliability and then compactness and weight. So like that. And if you are going for railways, again you need to first priority is weight and then compactness and then reliability and then efficiency and then cost. If you go for the UPS applications, UPS we will select for the household and some commercial applications, so where the cost is a major factor, so our priority is the cost and then life, and then compactness and then weight and then efficiency. Industry drives, cost is a major priority and then efficiency and then reliability and then compactness. That is how the driving factors are changing, and when driving factors are changing, now your topology you should select such a way that which you want as per that application. And then now we have discussed these things. We see that whether this converter is able to support like it can happen. Actually, in case of standalone, you see that solar to load, only we need to have a unidirectional. Always solar to the load. Your inverter doesn't need to have a bidirectional. But in case of standalone, what you do, sometimes you will keep a batteries off to get an uninterrupted. Standalone, there is no grid. If there is a grid, there is no need of batteries, additional batteries, because batteries are costly. Your grid is itself is acting as a storage. So you are having more power, you sell it. If you are having less power, you take it. And so the grid is doing like the energy storage. So it doesn't need additional batteries, because batteries are costly, and after 2-3 years, you need to have another batteries. Right? So this is costly, so that when there is a grid, you don't need it. But in case of standalone, there is no grid, you don't have some. If you want an uninterruptible power supply, then you need to have a battery. Then you need to have a inverter should be a battery sometimes. Getting enough. So like that, yes, this topology supports both, and it is having isolation. You can see that in the presence of the transformer is able to provide isolation. So it is able to provide isolation, and power decoupling is there. Yes, power decoupling means what is the power decoupling? Power decoupling is this. what happens is that your PV is able to give you DC, right? Your PV is DC. And what you want your load is AC. Yes or no? This is the voltage. You see that if I wanted to operate a windy power factor, then my current will be like this. Right? What is my power? Vm, Im, sin omega t into sin omega. Sin square omega t. Vm sin omega t and Im sin omega t at unity power factor. Right? So Vm Im sin square omega t. So what this is instantaneous power P of t. V of t into I of t. So now you see that it is nothing but what Vm into Im into what is sin square 1 minus cos 2 omega 2 by 2. Yes or no? This is P of. Right? If you do that average value, if I am finding out the average power means P, capital P are represented. P is nothing but Vm Im by 2. This cos 2 omega, if you do the integration, it will become 0. Yes or no? What is the integration of cos or sin? 0, huh? So we get only Vm sin of Vm Im by 2. That's why we see that what is the AC power? The average power Vm by root 2 and Im by root 2. So this is nothing but V into Vrms into Irms. This is the average power in case of AC. Alright. And now this is actually average power. Right? What about your input power? Input power is, what is your input power? VDC into VPV into IPV. This is the DC, this is the DC. Your DC into DC, if you this is the latest VDC, this is my IDC. If you multiply these two, what you will get? You will get somewhere DC, somewhere another DC. But if you multiply these two, what you are getting? What you are getting? Like this you are getting. So now, if you sin into sin square, is waveform, if you multiply, you will get like this. Are you getting me or not? If you take average value, it will be like this. This is again straight line. Why? Because it is V into I only. This V into I only. So this is average, but this is actually instantaneous. As we will design, your input power must be equal to output power. What we do, our average power is but actually what happens instantaneous if you see it, sometimes your this is my output power is higher. Sometimes my output is low, sometimes my output is higher. And if you see an average, both are equal. On average, both are equal. But instantaneous if you see it, sometimes your input is low, sometimes low. So whenever it is low, someone has to provide, right? Your input is there, 10, 10, but your output is like 0. So someone must be there that take care of this 10 and keep it. And whenever, now let us take your output, now your input is, let us take, your input is 10, but now our output needs 20. Now this 10 plus 10, 20 will come. That is how we are getting here limestone. Are you getting me? Some energy storage, some buffering action must be there. So this element we say it's the power takeover. This kind of now what happens is that you see this. If I can decompose like this waveform is having a two components. One is like this, another one is like this. Are you getting me? So this is the DC component. This AC component should be powered by some kind of a passive components. That if that arrangement is there, then we say that it is having a power takeover. Are you getting me? So like this. So yes, this feature is having because actually here we have these elements they take care about us. Okay, so all right, so it is having multiple stages, multiple stages are there, number of stages are more. So and it's having dual grounding. It is not having a dual grounding. It doesn't require option because we are having a transformer. Transformer is an isolation. Isolation means it will be more safe. So you're having some kind of offset current, DC current or something like that. It will not be reflected on another side. Transformer is low. Doesn't need it. So power and line component is medium because we are using high frequency transformer. This high frequency transformer generally you cannot go for high power. There is some kind of a problem in terms of a cooling and all. And normal transformer you are keeping oil cooling, right? But in case of high frequency design network doesn't require any instant cooling. So that's why we are limiting to the power handling. So how many number of components are there? There are 8 switches are there, 4 diodes that count I kept for the comparison purpose of that. More components, more cost, more weight, more value. And more switches means more switching losses. Like that. We need to segregate, we need to compare that. That's why I made size is bulky because more stages, more bulky. And the wide range of operation is there here in the more wide range is there. One is that because of duty you can control, and another thing is because of number of runs. So you can have a more wide range of voltage operation. And then cooling requirement is high because you are having more switches, more switching losses, more cooling. Getting more losses means more cooling. Symmetrical operation is both positive off cycle and negative off cycle are experiencing the same kind of arrangement, so it is very symmetrical. But some opposite they are not symmetrical. You see that. Right? And then filter requirement is there on a side. Yes, without filter you will not get a pure sinusoidal as per the grid codes. So it needs it. Complexity level is very less because more number of stages are there. One control action is taken care by one, another one is like that. Here are three control requirements are there. Let us take three converters are one will take one, contribute one. So if only one is there, the three has to handle by one, then it's more complicated. Like that. So more stages means less complex. Like that. Now you got idea about the features. Now we'll do similar kind of analysis for others. Actually, this converter, right? What we discussed, it can operate in two different ways. One is asynchronous and second one is synchronous. So synchronous means we can this is one stage, this is another stage. If you take these two synchronously, you can operate, or you can operate asynchronously. Means with constant same frequency for both, you can operate at different frequencies. Like a clock, you use it for synchronization. Here we are using carrier signal. Alright, so and now next topology is that you see that then the next research that they found that they are. Can you identify what is the difference between previous topology and this topology? We are getting a rectified DC. That is what they have found. That they have. You can see that here. They are trying to get a rectified DC here instead of constant DC, so that we can operate this inverters with the line frequency. This is line frequency. Earlier, this inverter is a switching frequency. See that this is a switching frequency, line frequency, not this is a switching frequency. Alright. So that is the one thing. Here we are getting a rectified times also. Will get these two per 0 to 10 milliseconds. 0 to 10 to 20 milliseconds. This will like that. So we'll get this can very easily can convert this. But again, the problem I discussed. When you are using this, you need to assign these components for higher voltage than previous topology. The beauty is that here they have reduced the burden on this part and they have increased the burden on this part. Regarding to what you want to do. Alright, this is the innovation. This is the new thing they have claimed when they published. This was in published in 1990. Alright. And then the similar comparison we have made. I kept it mostly in both the cases. Only thing is that your size is somewhat higher than previous one. This is the operation like we have seen, which is on. I given a color coding, you can easily understand. And I have also kept the switch. You see that these like pulses also I kept it, which kind of get signals from the MATLAB which I used, but I kept it also for easy understanding. And the next one, this is proposed by GE. So what is the difference? Can you observe from previous? The pseudo DC. Here there is no LC. Earlier there was L and DC. You remember? Now actually earlier what happens is that now this integral capacitor will not come for free. It will come with some cost, weight and value. So they are trying to eliminate that. But the problem is now the decoupling has to be done by this. Whatever decoupling I told, that someone has to take care. Someone means passive components. So now these inductors and the capacitor, instead of one inductor and one capacitor they are using here. Now whatever these two have, the work is done by these. Now they kept it here. Now you need to design changing the design of this field such that it should do functioning of filter. The main function of this is here to get a filtering edge and also decoupling edge. Like that, you need to select that and all right. So that is what this one developed by G for wind application. So like that is the equally it is applicable for solar. That's what they plan. Right. So that is how this topology. What are the like advantages that you are reducing this conductance numbers? But the problem is that comparison with previous two topologies, like you see that no DC link is required between that front end and output side. So that is there, and less cost, less size, less volume compared to the previous two topologies. These are of similar category. Right. Similar comparisons I kept it here. That this is the main difference. Alright, so next topology is that now, so far the three topologies which we have discussed, that basically they're doing the digital frequencies and then and now what they thought is that these others, the 26 France people, they proposed a transaction paper. They said that why we use this digital frequencies and frequencies. Why can't we go for AC to AC? Are you getting enough? Why can't we go for AC to directly? If you see frequencies, two frequencies, we are having frequency converters, we are having cyclo converter, matrix converter. What they can do? One level of frequency to another level of frequency. That is what earlier here what they, up to here it is same. You seen that up to here it is same. After the transform earlier we are having DC to AC to DC and then DC to AC. In it the AC to directly AC. Frequencies to frequencies. That is the claim they have. So I mentioned the color code. You can follow that when this will be on. Right? Understand? So this is the thing they have claimed when they have proposed. But what is the drawback? You say we have discussed the advantages so far, right? So advantage is that we are reducing one more place. Earlier we are using a frequency to DC, DC to AC. Then two stages. Now you see that a frequency to directly low frequencies, only one stage. Okay? So what is the advantage we will get? Advantage is that size weight value is that. But what is the drawback? The main drawback is that one frequency to another frequency when you are using the matrix converters, the power point is poor. That is the drawback. That they will not propose. That they will not mention in the class. That is we need to use. When we done the simulation, then we can understand. Well, you also know the fundamentals about cyclo converters. Why cyclo converters or AC converters are not so popular? Because when now I say that my input here my frequency let us say 10 kilohertz, here I want a 50. 10 kilohertz 50 hertz. Right? How many times? 10,000 by 50. 1000 by 5, 200 times you need to have a frequency conversion. You see that in AC to AC converter, if you remember the basics, want to either step it out or step it down. Like last time we will talk about voltage. Right? So number of cycles are increasing is frequency is decreasing. You want to increase the frequency or decrease? If you want to increase, you need to increase the number of cycles. So what you will do? You will do like this. Understand? So you see that whatever it is there, the same thing you will get it at the low. And whatever this portion that you will get is the negative cycle. So like this, you will get it like in one cycle you are getting a two cycles. So now frequency is getting double. Number more cycles, more frequency. Right? So this is not close to sine. It is like your fundamental wave will be somewhere. It is like deviated. Although you are converting one level, 50 to 100 I am making. Here there is 58, here I am making 100. But my output quality is getting increased. If you make it 3 times, you, like 150 also can make it, then it will be more poor. Although it is AC, it is 158 AC, there is no doubt. But your power point is going to degrade. That is the big problem. That's why these AC to AC converter, they, although they have climbed and they can do it, that's what they have proposed. But then, being a researcher, we need to investigate really, are you getting advantage? We'll get advantage in terms of compactness of this, but power quality, if your concern is the power quality, then you cannot select it compared to the previous one. Alright? So how it is operating during first cycle and interval cycle, that's what we are seeing. I mentioned here. Alright, so and what are the features of it? It doesn't need need any intermediate DCT. Actually, intermediate DCT, 1 year side DCT, you need to have alcoholic capacity. That is a bulky in size, weight, volume, also increases, and also decreases the life. So we are eliminating this means we are likely to somewhat. Only drawback is the power quality, but our main focus is the power quality. So you need to have a good quality of power, right? So that in that sense we don't use it. So bidirectional power flow is there. All the we see that on the topology we are having all the bidirectional switches are there. So inductor is a bidirectional, capacitor is a bidirectional. They were if you are using a switches for semi and they is all the bidirectional, then you get a bidirectional. In the topology we are having all the things are bidirectional. Yes, it is having a transformer and duty ratio to get a control of voltage, so we'll get a wider voltage range. And then isolation is there because we are having a like that I kept it, right? So that's what I mentioned here. You see that compared to earlier malicious, this is somewhat suffering from power consumption. And all the features like earlier we have mentioned. So you observe that one drawback is that it is more. See that here. Although number of stages are less, but here there is more switches are there. You see that in each leg actually, and cyclogram if you want to implement, need to have a 4-quadrant system. Right? You want a positive voltage, negative voltage, positive current, negative current. Right? So you need to have 4-quadrant switches. So that is realized with this arrangement. So more switches are there. That is another drawback of this. So like that. Next one is the conventional topology which we are referring in the morning here. This is like 2 stages. Now we so far we are seeing 3 stages. So far we are seeing 4 topologies. 4 topologies and 4 stages. After that, researchers they have done research and then they have proposed transformer. Yes. Here there is no any transformer. One is that stepping up and then distribution. This is a conventional topology which generally people will take to implement in this solar system. So we have a break for 10. We have a break for 10 and then
స్టార్ట్ చేసేసుకొని
తర్వాత ఒకసారి యూట్యూబ్ 5 minutes లేట్గా వస్తుంది కదా
2 minutes. ఇది నెట్ స్పీడ్ కూడా పెట్టుకుని ఉంటుంది.
మీ గైడ్కి కూడా ఓడియో వస్తుంది. మీ గైడ్కి ఓడియో వస్తుంది.
అవును ఓడి వచ్చింది.
ఈ అగ్ని వెళ్తామని
ఓడి పెట్టుకొని వచ్చేటప్పుడు మనం ఇట్లా ఉన్నాం అనుకోండి. వీటిలో పెట్టారా? నేను ఆల్రెడీ వీటిలో పెట్టాను. హలో హలో
హలో
వస్తుంది సార్. హలో వినిపించింది.
హలో హలో అక్కడ చూడండి. హలో మీరు ఎక్కడి నుంచి మాట్లాడతారు? దగ్గర ఉన్నారు.
హలో
ఏదో ఎక్కువ వస్తుంది.
హలో
ఎక్కువ ఏదో వస్తుంది. ఏదో సంగతి
ఉంది వస్తుంది.
ఏదో ఎక్కువ వస్తుంది. చిన్న ఇప్పుడు అలా వస్తుంది. ఇందాకంటే చిన్న అలా ఉంది. 2 minutes లేట్ వస్తుంది. మీరు బాగా పెట్టారు ఆపలేదు. మరి ఎలా వస్తుంది? టూ మినిట్స్ బఫర్ వల్ల చాలా చిన్నగా వస్తుంది. స్పీకర్ వస్తుంది.
స్పీకర్
చాలా చిన్నగా స్పీకర్ మరి ఆఫ్ చేయలేదు కదా? మరి ఎందుకు వస్తుంది?
రిసీవర్
ఫోన్ బాగా పెద్దగా
సార్ ఫోన్ కూడా వస్తుంది. బాగా చాలా క్లారిటీగా ఉంది.
పెద్దగా వేసింది
ఆన్ చేసుకోండి.
So now we'll discuss about our next topic. See that we have discussed the concerns from GCP and the AC topic. So now we see our next topology. So now you see the in this topology, the similar kind of features we are comparing. So what topologies we have discussed. Now similarly we are comparing the same features in this topology. It is having both independent as well as standalone operation capability. And also it doesn't have isolation because there is no any transformer in this topology which we have discussed. And then power decoupling is there. Yes, we are having power decoupling because we are having a boost converter and the boost converter is having the size as well. It is having a power decoupling. Number of cells are two. Earlier it is a multiple. Now this is the first topology which we are discussing in two-step category. And dual grounding will not support dual grounding because you see that we have these as right? So we have this is the element. So what does it mean by dual grounding? Now let us take our door, this is your home or whatever. If you are making it a ground, your input might be a TV or whatever. This is also if you are making it ground. Let us take. If you are making these three grounds, is it fine? It is not fine. You see that this is having a zero potential and this is also having the same potential. So this switch is always like it is a short. Understand? So this will not get an inverter operation. If you this conventional inverter topology will not support a dual grounding. So this is if you are grounding this, you cannot ground. Or if you are grounding this, you should not ground. Otherwise it will fail. Operation will fail. That is a big problem with conventional voltage to command with respect to dual grounding. So next one is that
Power handling capability is very high because it doesn't have any kind of a transformer or components, whatever we are using, like 5 6 are there, inverter core, some of them on, and then on the diode, and the capacitor, and the previous ones are there, no resistive components. And then size is bulky, some of the stages are single stage topology is not bulky, right? And the wide operating range is moderate, it is not having a it is only having a V control, so moderate. Only requirement is high because they are having 5 6 they are operating high high for the high requirement. Symmetrical operation, yes, it is symmetrical, we are cost of and then filter requirement is required without filter in that kind of power complexity of control is less whether this is DC, there are everything and this is synchronized system, so that's why this is good. Next topology where they have proposed is like proposed based on supersim. And they proposed an identity transaction. And then they proposed that to compare the previous topology, this topology DC to DC is now changed. DC to DC you see that earlier we are having a push number over here this alignment is changed. But what is the advantage is that you will get here these voltage rating and diode ratings compared to the previous topology in this case, you can take it off of the previous converter. You see that if these two devices are on, then D5 and D6 diodes will be off. And both has to block that. Off. Similarly, if these two are off, then D5, D6 will be on. The switches also blocking off of the voltage. That's why the rating of the switches will be slightly off than previous. It is like what I was studying sample tap and full bridge. In sample tap, we are having a rating higher than full bridge. Full bridge is lower. Right? So like that. This is what they have proposed and this is what how they are operating. Inverter is charged, like inductor is there. When we want to boost operation, then what we need to do? We need to store energy and then we need to pay that energy along with the simultaneously. So inductor is charging, this when switches are on, inductor will get charged, and when the switches are off, then inductor is alone is giving this purpose. If inductor and input is giving this stop. Here is the topology, the fixings of that. Okay. And then next topology they have proposed that is like two-stage isolated working space. What they did is that they are changing now the DC to DC stages. Previous topologies there is a non-isolated structure. Now they have changed with the flyback. This is a flyback. The same authors like they proposed a different paper. They have written their comment in previously presented, then they have written it was an earlier, so they used to get paper. So now they have the flyback and then the flyback is there, so you're having advantage that you're having wide range of operation because at least there is there to control more wide range of voltages. And the problem is that whenever this flyback transformer power is that's the problem.
But size will be
Size.
the transformer is size will increase.
Actually, sir, here compared to the previous topologies, in this case, actually the number of components are less. And it is very good for AC module. In case of AC module, which we have discussed in the sample stick and multi-stick and AC module, this topology we will be using the AC module. AC module will use a flyback based system. So because of this, you will get a higher voltage gain, and duty ratio is also there in our hand, and then we will result in voltage gain, more voltage gain is possible. So they will use this kind of component. So here also we see that it support both green and it is having isolation actually. And that power decoupling is there, yes, we are having an intermediate so it is having multiple stages, one is the flyback stage and second one is the digital system. Wheel grounding is not these two are it is yes and it is not. And power handling connectivity it is also limited. This case, as I told you, in this case power handling capability is limited because of this flyback. Actually, flyback transformer
is having energy stored there. Flyback, I mean, if you remember the flyback transformer doesn't need to store the energy. The flyback transformer is special and operates at full bridge DC cannot cast operates full bridge. Those cases would have seen the transformer doesn't need to store the energy. But in this case, flyback, the additional thing which you need to take care when you are designing a transformer is that you need to have high magnetizing component inductance to store the energy. We will store and we will take back the energy. So like that, so these are the cases. Alright, so that is actually a previous one, which we table, that's why it was titled that this is actually, this table is related to this. It's correct. So it is both stage isolation is there, and then for decoupling is there, number of stages is more, 2, and then dual grounding is not required. This is what I said. Right? That is all. Okay. And then another purpose is there, but boost and what about canal. There's one more. Yes, purpose and what about application. Solid application. You see that here, what is the advantage is that here it can be suitable for more higher. Although in earlier cases we have a transformer to take care of more voltage. Here actually you see that this capacitor is there. This capacitor voltage comes in series with your input voltage that is available at the output. So it is taking care of more voltage. So how it operates in positive and negative cycle, I have to right. So mode 1A and mode 1B is for buck boost conductor is there. This conductor to get charged and this conductor is discharging. That is what I saw. White means it is off. So how in which mode there is a 4 modes are there, and mode 2, 3, 4 it is discharging that and mode 1 is charging. So these are the features of this. Right. Body coupling is there. Number of stages are 2. Dual grounding is required. See that? And this dual grounding. Here in this case, actually dual grounding is required and it is possible also. Dual grounding is possible. Even you see that, even you ground here, nothing will happen. Because in series there is a lot of other stuff. So that will take care about you. So. And the next one is that this is a flyback converter with a decoupling. Right? So decoupling means here you see that this structure is there. Right? This you clearly observe it. Here, this I kept it with the color body. This one is the black one is a flyback operation, and the dash that the green is with the buck boost. Right? It is having both the features. Right? What happens in flyback when the switch is on? You see that. When the switch is on, the energy will be stored in the transformer, and the switch will be off, that energy will be given to the DC center. Right? That is how actually flyback operation. Also, you see that buck boost, if you remember, right? So this green one is making actually the buck boost converter configuration. Right? So it is having a both buck boost converter operation as well as flyback. It is having a more gain. So this one proposed by the Kaiser and then Siemens. This is like that. Denmark scientists, they have published the transaction from the so this flyback and then water we are doing. So here it is open for the example standalone. Like we have all the bidirectional features, and then if you want, you can bring power back from the grid to the input side. And yes, it is having isolation because there is a flyback operation like that. So power decoupling is there. It is the best actually because we are having, you see that, if you see it here, this capacitor is like exclusively we have designed to get a power decoupling. Right. So we have seen that excessive power sometimes we have seen this, right? So this is actually instantaneous power, this is average power. Whatever this excessive or whatever this less power is there, this power mismatch, instantaneous power mismatch, that is taken care by that capacitors which we have at CS. So that's why I have written it is a best.
I have a question.
Yes, sir.
For transaction purpose, is there any need to compare the previous hours or what they have done
No, that actually previous to what our proposals are there on the similar grounds, on similar features, we need to compare them. But transaction is essential.
all the previous work?
Yes. Yes. Simulation and mathematical. We actually with mathematical also we can get an idea. Mathematical modeling. There is some features, but if you can simulate it, then it will give you the more ideas so that we'll get a clarity on the analysis which we have done in the simulation. The mathematical simulation. Correlation we can be happening and then we'll get a good comparison. So for transaction actually it is a mandate comparison of at least 6 to 8 topologies. It is need to be compared. So like this size is low because we see that less number of components compared to the previous thing we have seen 3 stages and those cases is high. It is like that. So cooling requirements are medium and symmetrical it is very symmetrical because positive offset, negative offset having the same number of pattern. Right. So compressor is more because less number of cases. Alright. So next one is this one is more enhanced. Like see that if you observe it previous tuple and this tuple product focus the same Danish scientists. Danish scientists they have enhanced the feature of decoupling from their own pattern. And I see that the pattern they check again this buck boost and flyback. Right. So next one is you've seen that they like if you remember previously we have discussed DC to DC boost and then similarly it is like someone has proposed this is the outbridge and outbridge. You see that here earlier actually here there is a 2 switches. There are 2 switches now there is a 2 capacitors. These 2 capacitors also will give you the DC to AC power conversion. So what is the beauty is that here less number of switches. Actually switches is more what happens is the switch means not only switch. Switch means it is having a driving circuit. Driving circuit is more complicated to design. You need to have a sophisticated PCB design and you need to have a sophisticated control. Right? So those things will not can be avoided, but the main problem is real lifetime. So lifetime of the system is not good compared to the previous one. And this is a conventional, very traditional purpose. You know that. What is the good thing is that it is highly reliable, very reliable. And what is the drawback is that we are using a line frequency transformer. This transformer we are at 50 Hz. Earlier transformers also we are seeing that is their switching frequency. Now this is at a line frequency. Line frequency is bulky, very weighty, compactness, weight, all these are the drawbacks. Right?
Boost the switches.
So for that, for boost it is normal. Like MPPT will give you that switching power. It is like a DC. Yes. Simple code. Yes.
So we get the output and that will be compared.
Yes. Yes.
So that will be the pulses.
Yes.
But inverter is science and
Yes. So this is one interesting topology. So far, whatever topologies we have seen, the inverter side is having a stepping down. Right. So now actually this topology is very good. It is having a boost capability, inherently good. Doesn't have any additional DC to DC converter, but you see that will get actually a boost output. Here there is a load. What is the main idea is? You see the key idea. There is a 2 capacitors called C1 and C2. And there is a capacitor C1 and C2. You see that what we do, one capacitor It is a DC only, it is not AC, it is a DC. DC with some AC. Right? So similarly, in another capacitor, this is your VC1, this is your VC2. Okay. So our output, if you write the output voltage equation, V0 is equal to VC1 minus VC2. So here, this in this loop I write VC1 is connected to this and VC2 is connected to this. So I write outer voltage to conduct VC1 minus VC2. So if we subtract these two, in one VC1 is at the but let us take it is a VDC. This is a VDC. It is, I mean, if you write this in mathematical form, this VDC plus of like or VM, this we say VM. Okay. VM, this is entire thing is actually this entire thing is a VM, then it will become a VM by something. VM by sin omega. Okay. Here this one is VDC minus VM by 2 sin omega. It's like 180 degrees out of this. So if we subtract these two, VDC gets cancelled, VM by 2 minus or minus VM by 2 will become VM sin omega. You will get VM sin omega. Again, this is the key idea. So your input is a DC and your output you are getting a DC to AC, right? But you need to control the capacitor in such a way that it is like this. Right? Another capacitor should be 180 degrees out of phase. That should have a DC as well as AC components. Like that, this is the key idea. This is how they have the properties. So that is what. And the beauty is that here it can stepping up as well as and then right. So the next one is in this we can see the topology can be applicable for both standalone as well as the grid. Right? And isolation is there. Is it having isolation? No. There is no any isolation because there is no any transformer. Alright. So what is the next feature? Next feature is the power decoupling is there. Yes, very good power decoupling because that is having sinusoidal voltage on the capacitor. So it is there. So number of phases, VT is only one phase. With the one phase, stepping up and universal both are there. And then dual grounding is there. It is actually dual grounding is not there and it is not possible to see that. What happens? You see this in this topology. Let us take if I am grounding here, my load. Now if I am grounding this, then capacitor voltage is here. The load is here. And your capacitor is here. Your input is here, right? Assume that if this is grounded and this is also grounded, what is this capacitor voltage? 0. So you can never charge this capacitor with that voltage. So that happens in place. That is a big problem in terms of dual ground. Okay, so the next one is this topology has been proposed by this he is from Barbie, he is coming to Italy. Right, so they have proposed this topology. He is a professor at the university. He was earlier actually editor-in chief for the transactions and industrial transit. Okay, so and then the next topology is if you see that earlier the basic idea was with a boost base. Now it is a buck boost base. They have given a name is like force with buck boost model. So you see that the configuration is like a buck boost. You see that actually when your input is here, earlier you see that the input was here. The capacitor was placed like this. Here another capacitor. That is actually now that on there this is the proposal with some other scientist from RI. So as a number. Then they got it like it is having a stepping up as well as inverse also in the same set. That's why it's like four switches are there. And earlier cases except previous top previous any other top that is more switches we have experience. Simply the single space we are getting DC to stepping up is right? DC to DC and means DC to boosting and also inverse. Right? Alright, so this like these are the similar features we are comparing, and then the connection standalone processes are there, as well as not there, probably there, because we have a also that is decided for the dual grounding is required, but it is not there, right? And power line is high,
very small because of single cell operation. Is less limited because actually we don't have only one parameter to control the definition. So we say less.
Real grounding is required.
Actually, dual grounding is required in terms of we need to have a good safety.
Only safety point.
Safety point. As per actually solar PV systems, as per regulations of ITRA, they mentioned that if we are using a German standard, actually, they are following a German standard. If we are designing a solar PV system greater than 100 volts input, system should have either isolation or else it should have a dual ground. We don't use any isolation like some function or something like that. And topology should have this dual grounding feature. Otherwise, they will not allow you to connect with the grids. That is a grid code. When you are designing system, operating mode is greater than 100. That is the standard. Right. So the next one is that similarly, actually, they have changed some concept and they changed some idea also. What they have done is that here this upper portion is that we see that this is like generating a positive voltage and the lower portion is generating a negative voltage. And the output like they connected and like so you can see that at the output we are getting the full UVC. So means this is for the positive upper portion which are represented in yellow. And this some different color, you can see that is for negative option. So one the advantage is that yes, you are able to get the things in a single stage, but what is the drawback? You can see that is the utilization is less. Utilization is less, right? Because here this one is only for positive oxide, this is for negative oxide. Earlier another thing is like both positive and negative. So if you are using for entire duration, then you see that utilization is high, but here we are operating one part is positive oxide and the rest is negative. For negative oxide it is off, it is not doing any function, and during the positive oxide it is not in use. So we say that it is less utilization. Utilization factor is less of all the components. That is one drawback. And another drawback is that you see that in the input side we need to have a two decisions. Then only it will be possible to get this kind of operation. We say that three terminal DC power supply. Otherwise, you need to have at least 2 points. Then only will be able to get this. So that is the drawback of this. And then this one, like the similar features we have compared. It is like similar, like all the features are similar. Alright, so the similar idea they got it like earlier we have seen they have done with back and move or something like that. Now they got an idea why don't we use the same kind of idea to get with flyback. So they have done and they have thought of it and they have implemented and they got it. The operation that is possible with this flyback. This is a flyback based one setup and this is the other flyback. And then they are controlling this capacitor such a way that I told you we need to control this. I told that similar way they control it and they are easy to see in this isolation also they are having a wide range of voltage because RAM is also there and the rest of the circuit is also there. You have hand to control so you get a wide voltage. So that is what I mentioned like yes, red and isolation is there, coating of them is there because you have transfer magnetic capacitance, inductance and also capacitance, right? So that you have coating coupling and the number of stages are very similar and dual grounding is not required because already is having a transformer, right? I think so it doesn't need and power handling of volt is low because when you use a power this kind of flyback transformer it limits actually power handling because actually we need to have a in addition to the transformer feature it also need to have a this energy storage feature also. That's why typically it is got limited power in terms of power handling capability. So there is a small range of operations we have discussed. For cooling requirement is good because we are having only few devices on the calendar. So schematic operation during post cycle and clock cycle, the operation is very similar and as for requirement is required. Complexity level is more because we are having more than one stress. Alright. Next one is force switch resonant of bridge buck boost. This one proposed by this Lang and 14 references. I can see that what the idea is that the support of topologies that doesn't have this feature called resonance. Right. So we got they got an idea why don't we incorporate this resonance so that we'll have more efficiency. Because the resonance switching and all this, we have seen that when there is a resonance, we can improve the efficiency. That is what the idea, and then they found that they had developed this topology. You see that and it was like using less number of stages. Only thing is that they have incorporated one inductor on the second bridge middle. And how they control, I have given you that. You see that during positive half cycle, this will be off. You see that. The PWM pulses, you see that. Then you will understand. Here there is a PWM during negative half cycle, the switch. And here this positive half cycle it is switching, and negative half cycle it is not at all switching. And then this S2 is completely off during negative or positive half cycle. These two are off. So during positive half cycle, this switch is always on. You see that the switch is always on during positive half cycle, and then this switch is on and off at switching frequency, right? So now you see that now like this, the switching operation of the switches, and then we'll get to the anyway. The next slide I have, you can see that during positive half cycle there is a equilibrium circuit, during negative half cycle there is a equilibrium circuit. During the positive half cycle, you see that this is how this inductor is getting. You see that for see this will come like this, and like this, and like this, and like this. This is the closing part of the current. Similarly, during negative half cycle, this inductor is giving chance back to this capacitor. Right? Already there. So alright. So you see that yes, doesn't have isolation. It supports both UNF and bidirectional. So it can be used for built-in standalone both. Power diagram is there because you are having input side there is two capacitors are there, and the number of stages are single. The grounding is required. The grounding is not there. But it is required because isolation is not there. Right. So power handling component side only we are using power semiconductor device and simple and different capacitors. So there is no any limiting factor for the power. So we can design for high power. So the components, one more is extra here. Resonant element is the first time. You see that now the previous topology resonant element is here. First time it got introduced here, and then size is low. Cooling requirement is low because actually because of this resonance, our switching losses we can make it low. Right. So resonant switching is possible because the efficiency is good, and when the losses are low, our efficiency is high, the cooling requirement will be low. That is the beauty of this topology. And then symmetrical operation, yes, during positive half cycle and negative half cycle, you see that a similar number of switches and diodes. Right, so like that. And this is like another topology proposed by CASA. It is very much similar to the previous one topology which we have seen. And these are the features of this. And this, with the help of this bypass based topology, and then with this we are getting positive half cycle and negative half cycle, and then they got the recipe coordinates. And these are proposed by some proposals in the function. And then in this we are having isolation flyback converter, and it is like modification of outlet by boost converter, and it is using one application transformer and only 3 switches. It is applicable for only low power implementation of primary and electrons by frequency transformer. Right? These are the features for this topology. Right?
So what is the difference between high frequency and low frequency transformer?
So high frequency transformer actually the core, the way we design it will be different. In high frequency transformer we are having a ferrite course, synthetic course, and these things. Actually they are suitable for very high switching frequencies. When actually in high frequency transformer we need to operate at 50 Hz, but there we need to operate for 10 kilohertz or 20 kilohertz or 100 kilohertz depending on. And here when in case of high frequency transformer, when you are able to operate at high switching frequencies, then remaining component size, weight, volume is good. So in terms of transformer design, if you see it in case of iron 58 transformer we are using a CRGO steel, but in this case we are using this special ports, thread ports, some special alloys we are using to get this high frequency transformer.
So cooling requirement varies based on.
Sir, in frequency transform as well, because of this, even if they are operating at high frequencies, their losses are low. Sir. Because of these losses are low, we doesn't need any additional cooling methods like normal transformers. We need to have some kind of high cooling method.
But normally, eddy current loss loss.
Then in this engineering,
That is proportional to frequency and frequency.
because of the material, in iron it is like that. In that it is very low. And their BML is also changing the frequency on this thing. You see that overall frequency transform. That's why we are selecting such kind of a course. Yeah. In this iron frequency transformer, if you are changing the frequency, if you are increasing the frequency, these losses will also increase in normal transformer. But the core is completely different. So that makes a difference in terms of. Now next topology is that this is a one topology where we are having a asymmetrical operation. Positive half cycle it is operating like one converter and negative half cycle is operating like another converter. So because of that the components comes into the picture for positive half cycle is different and for negative half cycle it is different that we can see here. So this is the topology which are represented in blue color and green color represented. This blue color is completely it will give you the cut operation and then green color will give you the jet operation. You remember that this topology is derived with the idea of these two topologies merged and they got this idea. So they are converted. Positive cycle is like a zeta converter and negative cycle.
What is the data converter?
So it is one type of DC to DC converter like that.
What is the advantage of?
So actually the configuration is different, sir. It is also it is like the duty V by 1 minus G.
V by 1 minus. Just like a buck boost.
Yes, but buck boost actually will get a minus D by 1 minus G. Here it is inverting. There you will get inverting, here we will get non-inverting. So here we see that like it is useful for both and isolation is not there. Power decoupling is there because we have sufficient passive competence to decouple the power and number of stages is single. Electrode is required because we don't have isolation and power handling ability is high. We don't use any some limiting components of the power, so we can go for high power. Size is compact because of single stage. Pen drive the operation is there, and then cooling requirement is low, and then symmetrical operation is no. This is what I said. But previous topology, this topology, not symmetrical. Most of cycle it is like zeta and negative of cycle is like cut. So means things are different. Although gain is same. That's why we say that single is not symmetrical operation. And then we need to have some necessary recovery.
If the positive negative of cycles are symmetrical. So even harmonic different.
Yes, sir. Not like completely even on the harmonic. Actually, waveform is symmetrical about x-axis. Although the operation is unsymmetrical, means the operation is like zeta and cut, but we get symmetrical about x-axis, through which we are eliminating that even our harmonics.
So even though the data and the converter.
So gain is will be symmetrical about x-axis.
So even harmonics will be continuous.
Yes. And then next topology is a normal stage single stage series resonance. You can see that here they have used a resonance concept with a less number of earlier on we have seen one resonant concept. There actually we have used two capacitors at the input side and the middle like contains one inductor. But here those capacitors are getting only one capacitor medicine. And also these two thyrester, they are very slow devices, so the losses, they are not operating as system. So that is another beauty of this topology.
So normally, thyristors will not be equal to the system. Because along with the comma, they need the computational circuit also.
Yes.
But we are using the cost will be increased.
No, sir, actually here is actually where we don't use them is that, sir. In SCRs and all, because they are not self-completing.
Yes.
Because of that, actually we can only turn it on, we cannot turn it on. But in this topology which they are referred, they have proposed, that topology entire during positive half cycle one direction is on. They are not operating in switching frequency. They are very slow. Like in earlier cases, like 1 kilohertz, like 10 kilohertz or something, we are operating all the sensors. 10 kilohertz means it is like 1 by 10 milliseconds, means 100 microseconds. Yes, sir. So 100 microseconds we are operating at this. But here, each switch is operating for 10, 20 milliseconds. Earlier 10 micro, 100, sir?
20 milliseconds,
50 hertz. It is operating at very slow. Earlier 100 kilohertz, 50 kilohertz or 100 kilohertz or 10 kilohertz. Here it is only operating by 200 times slower. So in that case, we no need to go for high switching frequency devices, which are very costly. So that's why they have proposed this and they have utilized the SCR. Even the with slow responding device also the work, the conversion is possible. That's why they are SCR. So because of this, the main drawback is that here we are having punch switches and we are at PWM. And EMI is the one issue in this topology. We can see that is the main drawback of this topology. And because of this presence, here we have resonance, we are getting that was here which we have shown in topology. Switching losses can be decreased. So now another topology is that four switch resonance. This topology also based upon the resonance we are getting. This is the CR is the main component to get a resonance with these connectors. If you want to have a resonance, actually minimum you have 2 energy storage elements like 100 and more than that, even more than that, there is no problem. But minimum to get a resonance is at least you have 100. So this by using this CR capacitor in this inductor, so we are able to achieve a resonance in this so how these updates in each cycle are presented? These two switches, they are at line frequency, and these two switches are operating at during positive half cycle, this is now sleeping mode, and during negative half cycle, it is operating at switching frequency. Similarly, this one is like operating during only positive half cycle. Negative half cycle is like sleeping. Right? So this is how this is like switching. All these things are shown in the presentation of the gate signals I captured here, and then this is AC and positive half cycle. What is the equivalent circuit and negative half cycle? Here, which is just 3 is the PWM, as one is on, as 2 is completely on during positive. So you can see that is entirely on, and during positive it is entirely off. This is out and
Total duration that is should be on.
sir? Yes, sir. No, during positive outside this switch is on. During negative outside this switch is on. And during positive outside this is a switching frequency. This will be sleeping mode during negative half cycle. Negative half cycle, this will be at switching, and this will be positive half cycle. So these are the regular pulses of each switch and then influence of which during positive and half cycle are mentioned. Then there are the features like this is also based upon this one, because the pulling and the original element is here. And then assertion on the single phase, this one is down there, and high, size is low, is possible, And then the psychology professor at Bombay in 2008 or something, they proposed Professor Vivek Agarwal and their team, they have published one academic convention for the solar. This is also like basic ideas that this is one booster, this is one booster. So they are writing about this place. So doing first cycle, segregated in the green color and then growth cycle blue color. And easy to understand this blue color thing will be on the first cycle and green color thing will be on the growth cycle. And segregate by song you first cycle. We see that how the things are happening. During post-op cycle, what happens is that this entire this S4 is completely on during post-op cycle. During negative half cycle, this is entirely on, and these are operating in continuous. And during you see that during positive half cycle, this is on, this is off. So whenever this is now at PWM, S1. During negative half cycle, this is at PWM. Now you see the operation. Like this S1 is on, then inductor gets charged. When S1 is off, this inductor is through this diode. It is giving power to this load factor. Similarly, the same kind of things are happening with the help of our module, right? So these are the features. You can see that somewhere. Yeah, there is no resonance on some things. Including it. And then another topology is that high performance means like why they say high performance because these topology actually what they have proposed is that even under partial shading conditions also this is able to give you even this model is partial shading or this model is partial shading or both are not experiencing the same inclination. Still you are having a good quality of power and the nice performance. That is about the exam here. Who plays the role is that this inductor is a key element to get a good required performance. Right? How it is operating during the and then these are the features. You can see that for both and access is not, there. And the number of stages. Yes, this is the topology where you can apply it. You can see that you can also go so here we have a low side ground and also input side ground. So that is one of the systems. Here GL grounding is possible. Another trouble is that how bridge so this is like multi-level navigation. This also GL grounding is possible. Like see that how we are achieving the multiple levels, like first VDC and then zero level and reducing how we are reaching and how features are mentioned, but they mentioned there. Like this, and then the features of this topology, like you can see that this topology is also in terms of power handling capabilities, and also because we are having this topology is sort of multi-level, this is actually multi-level topology as well. The output quality is better than the two level in terms of the outputs, right? And also each device need to handle half of the voltage compared to the two level. Also common mode voltage will be off because we get low leakage currents and everything. That's all our PV systems. Alright, so and the next one is we'll discuss. We have another topology private class. This topology also proposed by and see that this software is containing the key idea is that what they do is S3, S4 is on, then you are getting a positive voltage. When S3, S4 is on, right, so inductor alone is experiencing a positive voltage. On the other side, when S1 and S2 is on, then your source polarity is becoming reverse, right? So S3 is coming in the negative terminal is coming here, and S1 is on, so positive terminal is coming here. So your input polarity is getting changed because of which you can get your output is positive. And you want a positive output voltage, S3, S4 is on, and negative voltage is required, and the negative cycle S1, S2 must be on the negative cycle, S3, S4 must be on the positive cycle. That is the idea that is how we send the polarity of supply, and then we can control these S5 and S3 such. And a PWM you can stop it up. That's why they say a transformer has voltage IC model. Alright, so this is the how during power cycle. I said that these two switches must be on. That's how they are represented. And power cycle is S1 has to be on. That's what we are discussing there. You can see that it goes like point of an. Alright, so these are the features supported with as well as the mother, there, and as a singer, and from the is not there, or high, so switches are 6 switches, we could see it, and then and then capacitors, and one frequency transfer, components. But you can see from the components. Size is low because of sensor, while the person is not there, because no mass gain, and then holding current is low, and then because some are operating at high frequency, and two are operating at 60 frequency, power losses are low, so holding current is low. Similar operation is yes, it is symmetrical between 1000 and 2000 is operation is symmetrical. Without filter system, control complex is more because of only synthesis are control. The next topology, this is the topology, the first time you can answer may go down. Results come down, alright, so see that compared to the previous example, there are 6 switches, but here there are reduced 1 switch less. Only 5 switches, so you can see S1, S2, and then S3 and S4 and S5, only 5 switches. Previous example, 6 switches are here, but here only 5 switches we are able to get the outcome. That is called the outcome. Right, so power cycle S1, S1, S5 are operating at same switching frequency and same PWM. S3, S4 completely on, allowing PWM. Even negative outside, S1 is at PWM, S2, S3 is somehow completely on, allowing PWM. That's how the equivalent happens and how this will get a see that if S4 is on, S1, S5 is on, and S5 is off, now see that there is a power. If S1 is on and S5 is off, our input and inductor And these are the features, and we have facility for compared with this, some patterns are more, but without layout, it doesn't need any layering or so on. So kind of so compared with this. Nice problems. There is another purpose they gave it is actual German patent. It is the given a name is a flying emitter. I would have heard about flying capacitor topology, flying capacitor multi-layer emitter. Similar kind of a concept here they have a lot and they have proposed they would be able to convert this into AC with flying emitter. Flying emitter, this emitter is flying. It is not like touching or positive or negative. It is like through this some astro this is flying. It is not like that scan. So like
Normally, playing capacity is there.
yes.
In the playing capacity, our capacitors are there, diodes will be there, switches will be there, based on the turn on, so we want to change.
Yes.
But why that is called flyback?
No, that is flying.
Playing capacity.
But actually, you see the flying capacitor property is like this. So, this is our actual flying. This is S1, S2, S3, S4. So there is different phases. This capacitor is the DC flying capacitor. This is not directly touching with your source. Or negative, this amplifier is also not directly touching. So it is like a flying, it is not directly touching with the one is your reference ground and another one is your source of the sky. It is in between, not directly touching with this or that. That's why we say it is a flying. It is in like floating. Depending upon S1 and S4, it will touch with the input or it will touch with the ground.
That is not directly contact.
Yes. There will
Based on
be
the switches only, it will not
contact. Yes. That's why they accept right. So that like that we have this here flying emitter. And then flying emitter actually there is three different operations we can get. That is what the German patent says, and even we can witness during positive outside, negative outside how it is happening. We see during positive cycle, we need sometimes our input to be lower than input, and sometimes output should be greater than output at the output. And negative cycle, we need negative and positive. And you can see that the basic all the DC you see that sometimes we need your input is less than we see this our requirement. This is our requirement. This we are having. This is my input that is straight. This is my VDC. This in this region, my input is all the output is always lower than input. So here we need to have a bar, and here this region we need to have a higher than your input. So here we need to have a bar boost. Yeah. And here always it is like here we again here buck we get. Here in this region, this compared to the input, it's having negative polarity. Like I told, buck boost is having this. Buck boost is like minus of d by 1 minus d times of Vn. If your Vn is positive, then your output is like negative. That's why you will get a negative off cycle. And duty ratio, by changing the duty ratio, it can be like greater or lower than the input magnitude, like that. And the key idea, that idea got implemented with this topology. We got all the things. This is what our requirement that is got fulfilled by this configuration. It can provide all 3D service. Accordingly, we need to switch them.
But in all the conductors, thermal inductors is will be required.
Yes, sir.
So, but the inductors are multiple functions. One is storing and discharging.
Yes.
That purpose only we are using.
Yes.
So based on that only we get the AC.
Yes.
AC voltage. AC voltage and AC current. To get that purpose only we are using inductor and capacitor.
Yes, sir. So this is what the topology is, and then the features of this. It can be used for both isolation, public number, and the number of services are single. Yes, we can see that. It can also ground here and also can be ground here. These are common ground. So we can have that's why this topology having a dual grounding like previous topology which we have seen. Last topology is also dual grounding. And then we can go for the next one is the boost neutral point example. So whenever this is also like dual grounding input side beam only can be grounded and load also can be grounded, and this is like gravity only level and all that, so somewhat better than kind of power only than previous two level and all this, right? So this is how we will get different levels positive voltage on these two switches are then positive EDC and then intermediate switches are on 0 level like that, and then lower switches are on and then again DC. So this is like that you can count this DC. This is the uses of this. And then there is another topology called six switch isolated values by 901 they are proposed. This is like some can I see that is there get required AC. You can see that. So how this circuit is operating during first power segment and two offset percent. And then we can see that during first power cycle, these ranges are on which we are getting the power transfer taking place during the power cycle. These blue color switches are on, that is how given the color coding for the circuit in this slide. That is how we can get this AC. And this is this topology is having as different.
Dark convention is there now.
Yes.
How to you want to wound different method?
What's that?
Dark convention is there.
Yes, sir.
So means the dark means current entering point.
Yes, sir. Sensing of finding how we wound.
We wound.
Yes.
Based on that only the dark will come.
Yes.
Phase and anti.
Yes. And the next one is that this is a Herrick motor. This one, this is a patent actually done by the Sunrise companies there. This is like compared to all inverters, this topaz is having a very good efficiency. That's why they gave a name, efficiency also good and good reliability. That's why they gave a name for this topology by this company called Sunbase. It is a patented technology. And then highly efficient and reliable inverter. So what they do is, there are actually when there is a power transfer has to take place from the load to input side. Actually, they are not passing back to the input side. They are actually circulating with the above these switches. That's why no need to send back to the input side actually. Whatever the freewheeling path actually that is being provided by with the help of this arrangement. Because of that, they are improving the efficiency. And also because of this, we are not sending back to the input side actually. The DV things will not be reflected on the switches and switches on the system base. So they are somewhat having good performance in terms of deliverability phases. Alright, and then it's operation during positive cycle and then negative cycle is being present in this slide. You can see that. And during positive cycle, which is around, and you see that in, as I said, these lag, new lag is being introduced, that is for the freewheeling path, right? So, during freewheeling path, main switches will not be no need to turn it on because we wanted to circulate the power between this load itself, right? don't need to send back the source side capacitor something like that. So that decreases the efficiency. That is how in positive side number and also negative side blue things becomes in the picture of this topology. Alright, so this is the thing. And then another topology is interesting than previous one. Here the leakage current, since we have discussed earlier, the leakage currents being not reflecting to this input side, they are subsequently hit. So now to decouple that in of these, they have disconnected over here. That is what this SMA can be. SMA, if you remember in the beginning, we have seen the market sort of this SMA is very high. So this topology is very good in terms of performance. They are not allowing the discharge current to flow to the input side. There is complete disconnect in the part like this. So this is pattern by SMA and this topology. That's what they call 4 5 switches. This kind of the power panel from grid during the current gradient period, that we have almost a constant common mode voltage that we can achieve in this. That is the leakage current will be reduced so that performance will be improved. These are the uses of this topology. And so far we have seen various topologies. Some topologies are good in terms of compactness, some topologies are good in terms of power decoupling, some topologies are good in terms of high efficiency, some topologies are very good in terms of reliability, some topologies are good in terms of weight and volume. This is what we are seeing. So based upon our requirement earlier at the beginning, we have been discussed that what actually the market needs. Different market need different parameter vectors, right? So accordingly, we need to select the topology which we have discussed over. We have discussed almost 44 topologies. Now just I will give you some idea. So far we have discussed single phase topologies. Now we have discussed more. So far we have discussed 38 topologies. Now I am just showing you 3 phase topologies in detail here. So similarly, whatever we have discussed so far, those topologies can be operation can be extended to 3 phase concept also. But now I am showing some other. One is that current source inverter. This current source inverter is having a boost capability, but the problem is that it needs to have this reverse voltage polarity devices. So that is the main drawback. And then the source, we have event source, which is having both advantages of enhancement voltages and current over against type of concept on voltages. And that's all things like support on relatively high current and voltage. There is another topology for gas from the front, and then this is like a with a boost functions. Remember, we have seen this kind of a pattern for single phase. Now they have extended for the three phase alignment, and they got a single phase. This is another CTP. They have developed 79 different topologies. Successfully, they got DC-DC autonomous synthesis. And similarly, another example, they have proposed by this Darvish based upon the Kirk concept. They have extended this Kirk concept of three phase with the low series of very there to become DC to three phase AC. What? Yeah, now this is a basic idea that how the DC can be like if you see that core idea of all this DC AC conversion. The core idea lies with the adoption of DC-DC converters. The extended DC-DC concept with the DC-DC. Even voltage source converter idea came from the converter. Like that, so various DC-DC converters which we have in the literature the beginning of this today's first session. So we are trying to avoid this. We need to avoid that. So, but in that case, actually, we need to have a topology which can operate with sufficient gain. Actually, another thing is that two-step programming only we need to see the solution for AC model. If you remember that we have four kind of architectures: called central and then string and multi-string and then AC module. Two-step ECUs programming units are a solution for AC model since they are required voltage amplification as well. Single stage PCU that we generally don't adapt with AC module because of the limited gain. Otherwise, you can adapt if it is having some kind of frequency based topology. And if several strings are connected to the grid, the multi-string concept is a very good choice compared to other string configurations. Electrolytic capacitors should be replaced or should be avoided to increase their level. That is what our point earlier we have discussed. These are the main culprit, these electrolytic capacitors actually. We can somehow replace this electrolytic capacitor with filling capacitors. Replace means we need to somehow size the capacitor such that the value of the capacitor should be low. Then only we will be able to get this filling capacitors. Filling capacitors are highly reliable than electrolytic capacitors. So either some topology they are avoiding this, or some topology they are able to allow this filling capacitors.
Either filling capacitor means
That is one type of capacitors. Electrolytic
we are in the between the two plates we want to place some metal
Yes.
or some plate.
Yes.
That is called filling.
Yes. There is different types of capacitor like filling capacitor, MPPF, and then ceramic capacitors and electrolytic capacitors, various capacitors. Among all these things, we see the chemistry for that filling capacitor they have very good reliability and lifetime. That's why we need to have some kind of a topologies which are able to design with the help of this filling capacitor. They have good reliability, or else somehow we should even less dependence of the capacitors. If we can able to design some topology, then that will be having ultimately good reliability. And then high frequency some topologies we have seen that high frequency samples will be applied for the voltage amplification. Right? That is very good for AC modules concept of right. So that is what we have discussed. Or we also say this AC module or microinverters or AC cell concept. And high frequency current source inverters are suitable for only low power, especially for AC module applications. High frequency voltage source inverters are suitable for both low and high power applications like AC module, string or multi-string inverters also.
So practically,
Yes.
current source inverters, where we use the current source inverters?
Generally, current source inverter we generally don't use because we are having all the time limitations. But wherever our loads are almost like a constant voltage and variable. If you are controlling the current controlled voltage source, that will be like a current controlled voltage.
So normally it is not used in practical. Only in theory point of view we use it. So but practically it is not. Normally voltage source inverters will not.
Yes, these are the references so far what we have discussed. All the topologies have been discussed. And then, as we have discussed in the morning also, we have seen that this agree voltage. So there is a various systems you can actually in this FDP. So there is a discussion on this agree voltage systems to optimize the land use. As we know that this agree voltage means agricultural photovoltaic systems, we have to optimize the land use for the electrical energy production. Right? So actually, when we are placing these PV modules, if you see that in the morning, let me go there.
So there is different configurations are there which we have discussed in the morning, like the reinforced regular mount or vertical mount or like flip mount, right? So there are various configurations we have, and we need to place them. You can see that in this figure. Um, every old like plant equipped with a dual axis and tracking. Right. So these arrangements which we have discussed in the morning, they in this paper what they have done is that they have adapted a mechanical tracking also. As we know that the sunflower is like rotating with respect to the sun motion. Like similarly, if you can rotate your PV modules as per the rotation of our sun, then we can our modules can be exposed to better radiation and temperature. Right. So once we are having better radiation, so we can get very good output. Right. So in that you can see it in like figure A, they have adapted that. And figure B, like they have used stilt unit. That's what we saw it here also. This one tracker stilt mount, the last one which I discussed, right? This last figure. And then equipped with 5 secondary axis and 10 solar panels. That is what they have shown in this figure B. And figure C, that stilt unit. This is a release 2 of the same. And the system equipped with 4 secondary axis and 32 solar panels. Right. So this kind of arrangement they have used. And then they have used the shading and radiation model to optimize the output energy production with the proper effective land utilization. So for this, they have developed this software platform, right? So and the data flow driven by the Scilab scripting is mentioned here. So you can see that the Scilab scripting this data flow. So they have adapted that. They have taken the inputs and then they are taking the sun position calculation and then sun tracking algorithm they have adapted, and then also they have calculated the shadows from the plant layout and panel shape. They have calculated this shadows calculation. And then weather files, like we have like NREL and all, they are giving a lot of data of the weather, right? So they have a huge data of the weather, particularly based upon the geographic location. All the data we can access, and then based upon that we can calculate new radiation, right? So and then modified weather files, and then GEC always model, it is processed there, and then crop output and soil output data, we can get it, that we can use it, right? So then this is the, like you can see that in this result they have presented air temperature and then rainfall in open air condition during the 3 periods of a simulated crop model. Right? And seedling, and then you can see that it's this figure from years 1976 to 2014. They have presented this, and so here actually phases duration based, like in global radiation and crop evaporation, they have put in these figures. And here you see the reference system in figure A is that this big figure is A and then support is B. Figure A like reference systems and rotating angles of the dual axis sun tracking. Delta voltaic is table 1 they have presented on it. This is the table 1.
presented in the beginning, and the various codes and syntax, all these things like tilt angle that have been represented. You can see that finally the height of the main rotation axis, calculate and ratio total final surface to the soil surface. They are calculated for these various configurations and they are presented here for this system. Alright, so and then they have estimated the electrical power and land equilibration. Well, and here also you can see that these earlier for four configurations they have presented, and then they have calculated earlier based biomass yield and then ratio aerobic energy to conventional. They have made it here. You can see from this table. And then crop simulation they have presented. And see that crop parameters and then minutes and values they have mentioned here. And from the references. These are simulated scenarios and conditions. And then they have presented the results. And also they have analyzed the effect of mean radiation reduction on the grain yield. This is like annual grain yield in the period 1976 to 2014 and see it on various scenarios. Right, so that you can observe here. And here like maps of seasonal radiation reduction to the workplace condition and simulated grain yield in 2 years. Right, so dry, drought and rainy. In 1987 there is a drought and in 2004 fully rainy seasons they have analyzed and they have presented the things. Biomass yield and energy production also they have analyzed. You can see that annual and season. And 1976 to 2014 they have presented. And then I can like this you can yeah, in the morning actually we have discussed such type of themes with the help of MATLAB. As we have this DP main objective is also like agrivoltaic and then EV integration that can be you can do better analysis simulations on the MATLAB. Right? So we have seen one of these Indian conditions like you can see it. They have various agrivoltaic systems. They have been installed in various places. This is what we have taken in the morning, 3 kilowatt system. And so you can see it. They like Agri PV rooftop in Bangalore they have installed for water pumping in case of for farming on the top of the home. So that is what we have done in the morning. We have done some analysis with the help of simulation. But we can do some more analysis on the simulation of that. You can see that like as we have discussed in the morning. Here, the first one is the torque and second one is the speed. Now actually we see that the speed is like we can see that there is a two currents. Here I have mentioned one is the stator current and second one is the rotor current. We can witness that when there is a speed change, then the current frequency is also getting changed. You can see that this waveform is having different frequency and this waveform is having different frequency. Yeah, means as I told you that here we have applied for the solar water pumping V by F technique, right? So that you can the speed is getting changed with the help of both see that perfectly it is like giving you the analysis. You see that I changed my radiation 1 from 1000 to 800. Same way we are getting this outcome. Sorry that. So this you can see that at point 1 at 1 second we have changed the radiation. That's why our BB module output power is BB array output is decreased at 1 second. You can see that. Even at 2 I have changed my load, but still the system is completely properly able to track the maximum power even under various load conditions as well as various input conditions. You can see that it is able to deliver maximum power that you can witness. And yeah, so this is what our reference for this water pumping. Like water pumping, the speed reference is calculated from here. This is the as I told you, in case of water pumping application, torque is directly proportional to the speed square. Right. So you see that is what we have taken. This we have taken from the pump which we have used centrifugal pump. For that they have given the data sheet. And the data sheet we got this torque speed relation, and this torque speed relationship we have implemented, and then that we used as a reference to generate the speed and then maximum power condition. There is a certain speed only we can able to drive at that given load condition. So that reference speed we are calculating, and that reference speed we are giving here, actual speed we are calculating, and then we are finding out the other to minimize that also to the frequency voltage that is being calculated, and that from that we are generating the reference. So that reference is sorry, that the gate pulses we are getting and this we can get.
Dear participants, let me summarize day 1 total sessions. So the morning inauguration started. After that, the session number 1, that is civil and mechanical aspects of a PV agri PV systems, that is completed successfully. Sir explained the nice way. The next is that is article discussion. Article number 1 and article number 2 discussed. And afternoon second session, sir discussed the solar cells or solar modules and applications of inverters. So I think these sessions are very helpful for your research work. Thank you for registering for this Atal FDP. And if you have any issues with accommodation or everything, you can contact me or co-coordinator Nagar Garu. We made all the things. You can stay here. You can attend tomorrow. Again, the sessions will start tomorrow morning. There is a sharp 9 o'clock. All of you assemble in the same seminar hall. So the 9 o'clock. So the day 2 will start. Thank you for listening and your patient listening for all the sessions. Thank you, all of you. Now we start the presentation. Today's speaker, Dr.D.RAVEEDHRA garu. I invite Rajini Madam, HOD of Vlits. Yes. Sir. You can do that. Thank you, sir. Thank you. Thank you so much. Thank you so much.
అంటే మళ్ళా మీకు నేను బిజీలో వెళ్ళిపోతాను సార్.
పెంట వెళ్తుంది కదా సార్కి చేసేస్తాను.